but not least day of our 3-day course organized by ISTS at Dartmouth and Google on Android malware analysis. And we're going to continue exploring different kinds of malware techniques today. Oops. All right. So today's schedule, we're going to start with Alec Girton, who's going to tell us how to reverse engineer pre-installed apps and also look at malware that creeps into the Android framework, not through apps, but through other mechanisms. And then we'll go on to code obfuscation taught by Vadim, and unpacking using Frida, also taught by Vadim. And then we'll wrap things up in the evening with lectures on other kinds of malware, namely proxy botnets, web scraping, DDoS, etc., by Roman, and using exposed for reverse engineering also by Roman. So as you've all already met Roman and Vadim, I'll just give a quick introduction to Alex. Alec is a reverse engineer on the Android security and privacy team, focusing on looking at pre-installed software that contains malicious, that exhibits malicious behavior. You've seen everybody else, and my sort of statutory legal reminder: the course is being recorded and will be distributed. So please note that, and that by being here, you are consenting to that. So without further ado, I'm going to stop sharing my screen and hand things over to Alec. Alec, over to you. Oh, and by the way, everybody, please mute your microphones, but feel free to ask questions through chat. And at the end of every lecture, please feel free, and I would strongly encourage questions, both through chat as well as verbally at the end of each lecture. Thank you. Over to Alex. Alec.
It's okay. I usually answer to both. So, okay. Welcome everybody to day 3. It says that I cannot share my screen, VS. Is there something I have to change? And you're muted now, so I can't.
Yeah, I'll go ahead.
You should be
and
good
right
to
now.
go.
Yeah.
You should be able to share now.
Okay. There we go. Okay. Okay. Can you all see the slides? Okay.
Looks good.
Great. Okay, so I wish I could say that on the 3rd day you get to rest your brains a little bit, but today is, I think, in my opinion, where things start to get a little weird or tricky. So in this first presentation, I was going to cover how to look at or how to analyze apps that are pre-installed on devices, and I'll explain why the process for that is different. Why the things you're looking for are different, and what the motivation for that is. So I think when some people think of pre-installed apps, you might think about, you know, aren't all these apps just coming from the Android open source project or from Google or from Samsung or whatever other company your phone is from? And people think, you know, shouldn't there not be any malware pre-installed? Or but the truth is that the supply chain for devices actually gets pretty complicated. And there's a lot of different people involved, and it opens up some room for malicious code to sneak in sometimes. So this chart here kind of shows the process for device manufacturing and all the different parties involved. And a lot of these lines tend to get blurred. So one company may be responsible for multiple steps in the process, which may also not necessarily be consecutive steps. But there's a lot of different people, a lot of different companies that all come together and all create different parts. So at the very low level, you have the chipset designers, be it you're like Qualcomm or MediaTek. that create the actual chipset, and oftentimes, maybe creating drivers, or even maybe even creating some of their own system apps. And then on top of that, you have the original device manufacturers, or the ODMs, the original equipment manufacturers, or OEMs, and they both work with third-party services or design shops, and they may get paid to pre-install certain apps. So sometimes when you get a phone, you might see, game apps pre-installed, or they might come with a certain theme from a specific company, where one company provides the launcher or the system UI, and maybe a bunch of wallpapers that come pre-installed, things like that. And so there's a lot of different moving parts that have to get audited. And each individual step could introduce malicious software or vulnerabilities. And so when you get a phone out of the box, there could be anywhere from 100 to 400 or 500 applications that are actually pre-installed, and you may not actually be aware of all these applications. Some of them don't even have user interfaces. Some of them are backend services for other apps. Some of them run things like notification services or alarms. These apps also tend to be difficult to remediate if they do have some kind of malicious or vulnerable software in them, because typically they're installed in places that are read-only. So if there is an issue, you may not have the option to uninstall it. You'd only have the option to disable it, and something else on the device could actually re-enable it. And the apps also get a lot more privileges, because their system apps are usually responsible for things like running the system UI, the launcher, managing other apps. On enterprise devices, they might have privileges for what they call device admin, which allows like the company to control the device. So if you get like a corporate phone, they may be able to control some functions remotely. And it's actually a nice target for malicious actors now, because you only have to convince one person to install this app and you get thousands of devices, as opposed to in some of the other instances we talked about in the previous lectures, you had to launch these huge advertising campaigns, or somehow trick users into installing your app. In this case, you just pay one person, or you convince one person to install an application, and you get all their users. And it can also, the last point I have on here, also can be a nice target, because exploiting the Android operating system has gotten a lot harder in recent versions. And when you pre-install your app, you can automatically get some higher privileges. So I think I already mentioned some of these things on this slide, but a lot of these apps are not going to be uninstallable. They get access to more sensitive permissions, especially depending on where on the device they're installed, and what if they're installed as a default app of some type, like the SMS handler or the web view. And if you can install one thing, you may be able to install multiple things pre-installed. So you actually get the opportunity to communicate with other processes that you designed or created. And this isn't very common when you're talking about downloading things from an app store or sideloading things, because it's hard enough to convince a user to download one app, much less 2 or 3. But in the pre-installed space, you can split up your functionality between multiple components, and they can all communicate with each other, and it allows you to separate out certain parts of what you're doing, diversify a little bit, and even provides a layer of obfuscation, because you have to have access to all those components to really understand what's happening. And some of these aren't always going to be available or aren't going to be visible to the user. They could be, as we'll talk about in the next presentation, some of them, some pieces of code that could be malicious aren't necessarily even going to be apps, or they may be apps that aren't intended to ever be used by the user. They're only supposed to be backend services used by the framework. So before we can actually start analyzing or looking at these pre-installed apps, we have to talk about the different format they're in. So generally speaking, this isn't always true, but generally speaking, when you get apps, if you pull apps off a phone that are pre-installed, they're going to be optimized or kind of pre-compiled in this format called codecs. And you have to do some processing before you get a traditional APK back. So before I jump into that process, I just want to cover some terms I think were covered in the first day, but I'm just going to briefly introduce them again. The first one is ahead of time compilation, and this is when code from the classes.dex or a dex file is compiled ahead of time and might be cached so that it can be run quickly. And this is as opposed to just-in-time compilation, when this is what happens by default when an app is run for the first time. It loads the code, compiles it on demand. And then profile guided compilation, I'll explain in the next couple slides. So when you look at a normal APK, these are the components you'll typically see. If you use APK tool to open it up, you'll see the manifests, a couple of different directories containing asset files, libraries, and of course the classes.dex. But when you look at an APK file that's pre-installed, the classes.dex is going to be missing. And that's because the classes.dex has been ahead of time compiled before you even turn on the device. So when you normally run an app that you download from an app store, or if you sideload it, these are the steps that you'll go through. You'll install the application and then launch it, which loads the classes.dex from the APK. And then you'll just in time compile anything that needs to be run. But first it'll check the cache to see if anything was ahead of time compiled from a previous run. And then over time, it'll try to figure out, the device will try to figure out what code is used most frequently, and it'll try to ahead of time compile the common code and put that in the cache. And that's where the profile guided compilation comes in. So each time you launch the app, the compiler learns which code is most likely going to get run, and it'll store that pre-compiled code that's executable by the Android runtime or ART. And it will just-in-time compile anything that it needs on demand that's probably less common or you don't use as much. So that might mean, for example, that certain classes, like if you use an app but you don't use certain activities very frequently, or certain functions in the app, then those may not get ahead of time compiled, or they may get kicked out of the cache eventually. And you'll have to just-in-time compile them when you do eventually use it. And it does this, when it does the ahead of time compiling, it'll usually do that during downtime in the background once it has a chance to analyze your usage. When you have a pre-installed app, however, there's a lot less steps. First of all, you don't have to install the app because it's pre-installed. And secondly, all the code is usually going to be ahead of time compiled. And so there is no classes.dex on the device. It's only in this pre-compiled format, and it's already cached. And the idea behind this is that system apps are probably going to be run a lot. And if you store the classes.dex and you're caching all that code, then it's stored in two places and it runs a little bit slower. So if it's pre-cached, you save space on the system image and you can launch apps faster. So if you go into your phone using ADB or something and you snoop around, or if you find a system image and mount it, you'll see a bunch of different files in the app directories. So the first one is the APK, which I mentioned. Looks like a traditional app, but it doesn't have the classes.dex. And then depending on which version of Android the device is using, you might see some of the following ones. The VDEX, which I think was only introduced starting in Oreo, is basically a decompressed DEX file. And it is basically used, it's similar to an ODEX, but it's a slightly different format that I think is supposed to allow for faster verification when it runs, because the code is actually stored separately from the APK. The device wants to verify that you're running the appropriate code and it's not been modified or anything like that. On older versions, you'll usually see ODEX, which was the first version of precompiled code. And if you Google around, you may see a bunch of other star.dex formats. There's pretty much one for each letter of the alphabet, I think, at this point. Like there's ADEX, BDEX, CDEX. But for our purposes, you pretty much only need to know these ones. And then there's art files, which are the representation of some of the code that's ready to be run by the Android runtime. And this is kind of something it can load faster. And so usually it's only a few select, I think, strings and classes. And there's one I actually left off of here, which is the OT files, which you may also see for depending on what you're looking at, which is OT files are just also precompiled code. So when we want to analyze these apps, we go through this process that we call deodexing, which basically allows us to recover the classes.dex file so that we can just load it in JDEX or load it in whatever decompiler you want to use. What we do internally usually is we take the original APK and we construct a classes.dex from the precompiled code and we shove it back into the APK. And if we want to look at the whole APK and if we want to have something that's runnable, we actually have to re-sign it because the signature won't match anymore. So you may have to use your own key, or if you somehow have access to the original signing key, you can use that as well. But you can just use Vaxmolly to do the conversion from the ODEX file back to original classes.dex file. And so I have the commands listed here for future use, but I'm just gonna go past this for now. This next section, I'll talk about some of the challenges that we face. They may not necessarily be challenges that you would face if you're looking at pre-installed apps yourself, though. And the reason for that is in our use case, a lot of what we're doing is at scale. And so we're not necessarily running these apps. If we're doing dynamic analysis, we're not running the apps on the original devices necessarily. We don't, go out and buy one of every possible model of phone and have a huge bank of phones that we're just running apps on. We may do that in some cases, but not in others. If you have the original device, you can obviously run the app in the intended environment. But when you're running these pre-installed apps on an emulator or on another device, they may require things that were system modifications on that device, specific to that device in order to run. So this could be things like maybe they need specific device drivers, or they need specific hardware. They may even need specific versions or modified versions of the Android framework code, or specific binaries that are installed on the device, or other apps that are installed on the device that they have to work with. So if you try to take one of these apps and pop it into an emulator, it may not necessarily work. The example I have here shows a case where you're trying to take a pre-installed app that you found and load it onto a device or emulator that already has that package. So if the app with the same package name is pre-installed, you can't just install another one over it, especially if it doesn't have the same signature. So if you're trying to run these in an emulator, you may run into some issues, and there are some workarounds, but they can be time consuming or difficult, and have a lot of problems. But you can try signing the apps with your own key if you build your own Android image and run it on the emulator. Or you could try, if you have access to root, you could try putting them in the system partition, which is usually only read-only, but in a user eng build or an emulator, you might have access to root, in which case you can remount that partition. Okay, so now actually reverse engineering these or analyzing these. There are some things that are just inherently different about pre-installed apps. And the first one is shared user IDs. So in the manifest, you can specify that you want an app to run with a specific user ID. And in this example, I've shown how to specify that you want the user ID to run as the system user. So any apps that specify the same shared user ID will run as the same Linux user. And this means they'll have access to the same set of resources. In particular, one thing that's important is they'll have access to the same permissions. So if I create one app that runs as a specific shared user ID, and I say I want to receive SMS, and then I create a second app that also runs with that shared user ID, and I don't actually have to request receive SMS. I already get access to it through the other app. In order to use the same shared user ID, though, they have to be signed by the same key. So they have to use the same signing cert. But this is really uncommon to see not pre-installed, because like I said, usually it's hard to get someone to install multiple applications if you're trying to do it maliciously. So, but pre-installed, this is very common. And then some of these shared user IDs are actually reserved. So for example, this one, android.uid.system, actually runs as the Linux system user. So if you're using a command line tool like ls-l to see the user and group of a binary, for example, and it says system, that would be the same as this. And it's the same user that all of the Android operating system framework code runs as. So you will run with all the same permissions as basically the operating system mostly. And a lot of the pre-installed apps will use the same user ID. But there are also or allow you to communicate with other apps that share parts of the functionality of that of the phone or of the system UI. So like, for example, some manufacturers may split up the phone into 3 or 4 apps even. So you might have one that's the dialer, one that is your shows your call history, and one that does backups or something like that. And together, all 3 of them actually make what the user sees as the phone, but it's just split up between 3 different APKs that are all running as the same user ID. So in particular for the system user, one thing that's important to see is that some of the code in the Android SDK is only available to be run by the system user. And so if you look in the AOSP source code, you'll see these annotations at system API. And these are only able to be run by the system user. Generally speaking, most of the time, I think they're only meant to be called internally by the framework code, but apps that run as the system user are also able to call them, although I think it has to be through reflection. And you also see, in this example, it requires a specific permission, but like I said, if you're running as the shared user ID, then you have access to the permissions that other apps with your user ID declare. So usually that might not be a problem. So this annotation for system API is actually, I think, a superset of the hide annotation. And so if you're looking at developer.android.com, you actually won't see these methods or classes showing up in the documentation. You'll only see them in the source code. That's because usually for developers, they're not accessible, but when you're working pre-installed, you may be able to use them. And you will find a lot of these methods in classes that have other methods that are publicly available. So if you look at the package manager, the Bluetooth manager, any of the normal system services you might use to access excuse me, framework functionality, you will find these extra methods sprinkled in. Sometimes they're meant to be internal methods, but callable by other classes, so they're not private, they're public still. But system apps will be able to access this. Another difference is the prib app directory. Most of the apps, especially if they're not necessary for critical parts of the operating system's functionality, will be stored in /system/app on the device. And so this might be anything like I said, like any pre-installed games, anything that you wouldn't normally, anything that's maybe specific to a particular device manufacturer that's not part of the core operating system. Anything that's a fun feature like a wallpaper app, or what's another good example? I think launchers can be installed here sometimes, things like that. But in the prib app directory, you'll find a lot more of the apps that have sensitive functionality or need extra permissions, and they actually get access to an extra set of permissions, some of which I've listed here, but there's actually a much longer list. So read and write secure settings will allow you to access a extra set of settings on top of just the normal read and write settings. So secure settings include things that are more sensitive, like disabling Google Play Protect antivirus, or enabling side loading, or it could be enabling or disabling other security features. And then reboot and recovery allow you to reboot the device and launch in recovery mode, which is used for updating the system image or updating the device. So it's for system update apps only. Okay, so that's more or less how to take a look at pre-installed applications. If you're interested more in how the compilation process works, I would take a look at this first one, but beware, you can go down a rabbit hole really fast. If you still need to download Smalley or Box Smalley, go ahead and take a look at the GitHub repo here. And the last one shows you a little bit more in depth of how whitelisting for permissions works, or how pre-granting of privileged permissions works. And that's all I have for you right now. Do you have any questions?
Thank you, Alec. That was great. So really, there are some questions that have floated through on chat. And so maybe I can read them to you and have you answer them.
Yeah,
Or you can see them.
I can see them now. I just couldn't see them while I was presenting.
Yeah, of course, yeah.
Okay, when would apps want to use the shared user ID? Why is this feature useful? Okay, so the answer there really depends on whether you're a malicious actor or not. A malicious actor, it would definitely be useful because you can split up your functionality and you have your apps collude with each other, and it kind of acts as a level of obfuscation. It also might be an assurance in case one of your apps gets uninstalled. You still have something on the device, or like a foothold on the device.
Right.
When you're talking about more legitimate use cases, in the pre-installed space, I think I covered the system user pretty well, but and I think I also mentioned with other cases like the phone, you might want to split up your functionality between a couple different apps. But in general, I don't see this being used very much outside of the pre-installed space. I do see sometimes OEMs adding their own shared user IDs, but they're usually also in similar use cases where they split up functionality for one core feature into multiple parts. Yeah, I don't usually see this in any apps that are sideloaded or like on the Play Store. It's usually just a way for developers to kind of silo certain parts. So like one app may act as a service that provides core functionality to multiple apps, for example. And it kind of acts as like a server-client relationship, which there are other methods on Android for doing that, but that's one use case. Did that answer your question?
Yeah, it does. I guess my reservation over here is that if you have, let's say, for example, a large social network company that controls a bunch of apps, and in such cases, like most people have like at least 3 or 4 of their apps installed on their phone. So it sort of makes me nervous that they can, given that they would have access to the same signing certificate, they can actually collude between their apps. So it sort of makes me wonder why this was left as a feature for developers rather than just OEMs. Do you have any idea about that?
I don't really have much insight into the why, honestly. I don't know if Sebastian or someone else does, but yeah, sorry.
Sorry, what was the question?
The question was, why are shared user IDs allowed in user space as like normal user apps as opposed to just system apps?
I do not know the answer to that, I'm afraid.
Yeah.
Yeah, it's just something I wondered about, given like large corporations do control a lot of applications, so it sort of leaves a pretty big hole.
I will say that I think a lot of Android features like that have roots in the earlier days of Android that where they really wanted it to be as flexible and like user modifiable as possible. And so I think some of this might be related to things where a user wants to install, wants to create their own look and feel on their device. So they might use download multiple apps from a third-party service to do like a new system UI or a new launcher and a new wallpaper app and things like that. And so that they can kind of almost overwrite the UI of the original manufacturer. So I think that might be one of the intended use cases. But
Thanks. Yeah.
yeah, okay. If P is a pre-installed app which uses a shared user ID, and later the same app developer deploys a non-pre-installed app P, would that mean that, P prime, would that mean that P prime would have the same privileges as P, i.e. system access? Yes, I think is the answer, basically, the short answer.
That's what I was afraid of, yeah.
Yeah, so I think essentially if you have an OEM that releases their original device, I think they can push, or if you can, like, for example, like go to their website and download another app that uses the system user ID. And as long as it's signed with the same cert, I think it would still be able to run. I'm probably like 85 to 90% sure on that one. Not 100% sure, but I'm pretty sure. You mentioned that a pre-installed app has access to permissions like package managers. So does that mean a malicious pre-installed app could uninstall any app the user might have installed on the device? Yes, is the short answer. And I think one thing I actually forgot to talk about a little bit was the more common use cases we see pre-installed. And one of those is hostile downloaders. And so those are cases where a pre-installed app might be installing apps in the background, whether maybe they're getting paid to install applications, or they're specifically installing apps because they are doing some kind of ad fraud, or and they're getting, like I said, they're getting paid for those downloads, or they're trying to download apps where they know there will be ads that they can click on. And then frequently they also uninstall those apps. I don't think I've really come across cases where they're just randomly uninstalling apps to annoy the user, but usually there's a little bit more of a nefarious purpose than just annoying the user. But yes, it is possible. And I would say cases where that I would expect that might happen are where the user may install, I don't think I've seen this happen, but the user, maybe they would want to uninstall something like an antivirus app, for example. Yeah. In the supply chain slide, what exactly is an ODM OEM? Good question. I have not seen a good, perfect definition for these, but generally speaking, I think of the ODM as the person or the entity that actually created, like designed the device, and the OEM as the company it's shipped under. So what would be a good example? There are certain devices that you can get where you may notice that two different devices are shipped under different brand names, different companies, different model names, but look identical, except maybe like a few modifications, like some different pre-installed apps, or some, they come in a different color. And that's because the OEM has a licensing agreement with the ODM where they basically purchase rights to add on to a device and ship it as their own. And you may also see this in cases where there's one parent company that has multiple brands. So you might see some of the larger, like Chinese OEMs, for example, like I think Oppo and Vivo are the same company. Techno and ITEL are both transient. So there's a couple different cases like that. I hope that answers your question. And that's not always a perfect definition. Like I said, the lines get blurred a lot and different companies have different processes, but that's generally what it means.
That answers my question. Thank you.
Great. Oh, and apparently the last thing says that shared user ID is going to be removed. Interesting, I did not know that.
I just searched the web and they say in the APN level 29, it's going to be deprecated or removed. And they say it's the shared user ID. It's, I mean, from the post, they say it's like a shotgun or something. They say the guy doesn't recommend the user or the developer to use it.
Yeah.
They say, they just mentioned maybe IPC or this kind of thing is better than the shared user ID.
And I think that's generally how I see it being used a lot, at least outside of the standard like system user ID, is, you know, it being used as a replacement for standard IPC, like instead of binder. And so I think that that would make sense that they would be deprecating it to try and promote use of binder or other methods.
Thank you.
Yep.
I have one more question.
Sure.
Is it possible that we can somehow randomize the system user IDs so that these kind of attacks not happen? Like if I have a rooted phone, can I go around and randomize the user IDs of these apps and will the phone still work?
No, I don't think so. So for all of these predefined ones, I think they all have predefined values. So like, for example, the system user is actually the Linux system user, which I think is ID of 2000 if you're looking in LS results. And for user space ones, if they're not these ones that are predefined in the Android framework, those are assigned dynamically when the processes are created, I believe. But if you go around messing with the system ones, then it's going to break things.
Okay, thank you.
Yeah.
More questions?
So let's say that Google, I'm using a Google phone and I'm trying to install a Google app later on. And so obviously, since it's a Google application, it can use the shared user ID and then gain access to basically my entire phone, right? Because virtually, is that assumption correct first?
Yes and no, kind of. So I wouldn't say it would, you know, have access to the whole phone. Most of the Android system, or most of the system apps on a device are going to be signed with the OEM key, which Google would not have access to. So the pre-installed Google apps I think would be signed by Google. But those are majority of the apps you'd be downloading from Google anyway. So like the pre-installed Google apps would be like Gmail, Chrome, things like that. So if you're downloading another Google app that wasn't pre-installed on your device, then in theory, it could use the same shared user ID. I don't think Google apps do that though right now. I have seen some cases though where OEMs will publish like for example, like a system diagnostic tool or something that's downloadable by users, so that you can add an app to your device that'll have those kind of system privileges. But generally speaking, I don't think it's very common for side apps or App Store downloaded apps to use those shared user IDs.
Mm-hmm. So I guess my question is that the app would not, so the permissions that the newly installed app requests if it is using the shared user ID, it doesn't have to, like the phone isn't really going to prompt me for these permissions, right?
I don't think so.
So I guess my question is there any way of maybe intercepting these permission requests using like the binder layer or something to even know that the phone is doing something like this?
By intercepting, you mean like making the user aware that it's getting these permissions automatically?
Yes.
I'm actually not sure how to answer that question. I haven't actually looked too much personally, at least, into this idea of side loading shared user ID apps. I've only looked into it a little bit, and so I haven't toyed around with it very much. But so I'm not really sure if you can or not.
So Alec, I mean, the sort of take-home message that is sort of floating around in my head, at least, is that this shared user ID is basically potentially a huge problem.
It can be, and I
Right.
think a lot of it can depend on the operational security of the device manufacturer, right?
Right, right.
So how secure is their signing keys, or other apps that they've been developing, or yeah, if those keys get leaked, then all is lost.
Right. It's like a single point of failure.
In a sense, it can.
Maybe that's why this. That's why this article is talking about it's disappearing. Which.
Yeah.
So on the flip side, what problems would legitimate developers have that we haven't talked about if the shared user ID disappeared?
I could only see problems in the pre-installed space that would be pretty specific to the actual Android architecture. So I would assume if they were removing it, there would be a replacement of some kind.
Right.
Because they're the majority of the use cases I see are basically things that are baked into AOSP.
Right.
So I'm not really familiar with how they're removing it, but I would think that there'd be certain things that have to change regarding apps, at least apps running as the system user.
Got it. All right. So sounds good. So I think this has been a great session, Alex. So we'll use the opportunity to take our usual 5-minute break and between sessions and reconvene. So thank you for a great talk, and for everybody else, let's reconvene in 6 minutes. It's 12:54 Eastern here, according to my clock. So we'll reconvene in 6 minutes at 1 o'clock Eastern, and listen to Alec talk about malware that's not sitting in apps. So see you all in 6 minutes, guys. Thank you. Great talk, Alec. Thank you. Let's reconvene. It's 1 o'clock according to my clock, and it's Alec on again, and he's going to be talking about malware, Android malware that is not basically an app of some sort. So over to you again, Alec.
Great, thank you. Give me just a second to share my screen. Okay. So I alluded to this in the last presentation, but one of the things I think makes the pre-installed space really interesting is that you can have, if you're a malicious actor, you have the possibilities of getting multiple components baked in, and not just an individual app. And you can use this to do make your code more obfuscated, to get different privileges that are even greater maybe than a normal system app. And there's a bunch of different use cases. In particular, one that we see a lot is persistence. So if you have multiple components pre-installed, you can ensure that you're always going to be able to have something on the device. So if you have something that's not removable, you have a foothold where you can keep re-downloading your applications onto the device. But before I really get into the details of the malware, I'm going to talk a little bit about what you'll see if you actually look at the internals of an app or of a device, or if you get a firmware image from somewhere on the internet. And so if you get a firmware image, it's usually split up into a couple different parts. There are more parts than I've listed here, but these are the main ones that we're going to be concerned with. The first one is the boot partition image, and this contains the compressed Linux kernel and optionally a RAM disk image, so that is basically the core of like the Linux operating system. Right here is you boot up the kernel and then you load the file system, which is going to be stored in possibly a couple different partitions. The main one being the system one, which is the core of the Android framework. Everything that's from AOSP is going to be in here. And then usually anything that's a modification on top of AOSP will be here. The vendor partition is supposed to be for anything that's added on top of AOSP, like any binaries or applications that are created by the OEM or the ODM or anybody else in that supply chain. But this isn't strictly enforced, so the lines between system and vendor get blurred quite a bit. The other two aren't going to be as interesting necessarily for actually unpacking or analyzing. User data is where everything gets installed once or by the user. So it's not necessarily going to have anything interesting right out of the box. And then recovery is used during the system update process. So during system update, you'll boot into recovery and mount a new system image with all the updated applications or binaries or Android framework code. When you find these images originally, they're not necessarily going to be in a normal Linux format that you can just mount on your machine. Sometimes they are, but generally speaking, they come in this specific Android sparse format. And it's really just it's more or less just a simple compression tool that takes out the unuseful or repeated or blank chunks of this image because they want to make it smaller so that they can transfer faster over if you're downloading a system update, or if you're using a tool like Fastboot or ADB to actually put a new image on a device or an emulator. It's really just a space saver, and it actually is a quick transition back and forth between this Android format and a normal Linux like a XT, sorry, like a X4 or something like that. So if you get a system image from somewhere and you take a look at the file format, usually you'll see that it says it's this Android sparse image. There are exceptions, so I always check to make sure what format it's in before I start working with it. If it is in this Android format, there's a tool called simage to image, which converts it from the sparse image to a normal Linux mountable image. And so if I'm working on a Linux or POSIX machine, I'll do this first and then create some kind of directory on my device and then just mount the image directly. So in this case, this system.image is actually the image for the system partition. And that's where the core, the meat of most of the operating system is going to be. In some cases, I may also look at the vendor partition or others, but like 90% of the time, you're going to be looking at the system image. Once you open up this file system, there's a couple directories, some of which may look familiar if you're used to Linux or Unix systems. and some of which are added for Android. The first two I think we talked about in the last presentation, the app and priv app directories, and that's where pretty much all the APKs are going to be. Sometimes you'll see a few other directories. I've seen sometimes ones called pre-installed or preloads. Sometimes OEMs create their own directories where they put some other apps separately from the others. I think pretty much just as an organization technique. Then the bin directory, there may also be an sbin or xbin directory, but this is where all of the Linux and Android tools are going to go that aren't basically. So this could be daemons that are run. It could be shell scripts. It could be, just normal other tools like diagnostic tools, things that are binaries for factory testing before they, like for quality assurance, before they ship out. In Etsy, you have all of your normal Linux and init scripts and things like that. And there's also on top of that going to be some things added by Android, like the configurations for pre-granting permissions to system apps. So like out of the box, you're probably going to want, your pre-installed phone app to be able to call people, things like that. One other thing that may be important later is the SE Linux rules. So the SE Linux rules, if you're not really familiar with what SE Linux is, it's a protection layer that more or less allows you to specify which processes are going to have access to which resources. So you can lock everything down by default and then say, okay, maybe the netd daemon is going to need access to, the networking stack or the networking hardware, or, this process is going to need the ability to create sockets, things like that. In the framework directory, that's where you're going to find all of the compiled code for the Android framework, the SDK. So this is also going to be usually, or it should be at least, odexed. So you can still use Backsmally to get the original DEX files, and I'll cover that in a little bit. And then the last thing is the lib directories that contain all of the ELF libraries. So these could be things that are part of the Android operating system or are used by the Android framework. So you might see things in here like libsqlite, that's used by the Android framework for providing databases for applications. You'll also see things here, I think, like libart, which is the actual ELF file that contains the Android runtime and is responsible for doing all of the ahead of time and just-in-time compilation that we talked about in the last presentation. So let's start by talking about the framework code. So in that framework directory, you're going to find a hierarchy, a file system full of VDEX or ODEX files that contain all the code for any of the classes that you would normally use in Android Studio that start with this android.star. You may find other things like anything that's dynamically linked, like maybe some of the Google classes. There could be classes linked there by or put there by the OEM for that interact maybe with their specific device drivers, things like that. So this would be like where your package manager, your Wi-Fi manager, all that kind of code would be. In addition to the stuff that is exposed to user applications, you'll also find a lot of internal classes, and this could be the things that are all the like helper classes that are used by those user-facing or developer-facing APIs. It could be things that just run in the background that receive events from the kernel. So this is how you have the hardware abstraction layer of as part of the hardware abstraction layer with communicating with device drivers and apps. And you'll have things that are specific to the chipset. There's a lot of different possibilities in here. And so deodexing here is pretty similar to deodexing APKs, with the exception that for some cases you may have to, some of the symbols may be only stored in this boot.oat file. And so sometimes you have to specify the path to that file when you're deodexing another dex file. But there's documentation on how to do that on the GitHub page for Boxmolly. One thing I recommend if you're working on Android Oreo or later is using this tool called VDEX extractor. It combines a lot of the steps you might normally do with Boxmolly and Smolly into one process. And so basically you just pass it the VDEX and it creates a normal DEX file for you that you can just load in JDEX. Whereas with, if you're using Boxmolly, you might have to do, use Boxmolly to disassemble and then Smolly to reassemble, and it's just a lot more steps. Okay. One of the things that's interesting to look at in the framework code are these system services. So in the example code line here, I was showing how an app might get access to the Wi-Fi manager. When the app has the necessary permissions, it can get an instance of this Wi-Fi manager class, and then it can call a bunch of methods that actually get run as the privileged system user, but it's run on behalf of the apps. So when you call into a method to Wi-Fi manager, it'll say, do you have the necessary permission? Okay, you do. I'm going to run this the rest of this method as my own user and not as the calling app. This gets interesting because when system services get added, it's an opportunity to look for things where there are maybe mistakes or malware. In particular, I've seen some cases where devices ship with a system service that is basically a proxy to use a bunch of other services like the Wi-Fi manager or package manager, but without checking for the permission. Or they may check for a custom permission that was created by specifically for that device. I've also seen cases where a system service is added to work with an OTA solution or another application that's pre-installed. And sometimes that application, because it's developed by a third party, may have malicious code that runs in it, and then all of a sudden has a backdoor into the framework code. So I think one of the samples that I'll show you guys actually is a good example of that. If you want to try to, using some of this on a device, it gets a little bit tricky because normally things like the Wi-Fi manager are included in Android Studio as part of the SDK. But if you have a service or something that's that's created specifically by an OEM, then when you're developing an Android Studio, it's not going to know what that class is. So in this case, I just made up a random system service that's maybe added by an OEM. And let's say I want to try making an app, a test application, to make a proof of concept for some vulnerability or for some malware. If I'm trying to make that application in Android Studio, by default, it's not going to be able to compile because this OEM manager class isn't part of the Android SDK that Android Studio has. In some cases, OEMs will actually publish their own SDK that you can load in Android Studio to be used by developers. Sometimes, though, you have to be specifically registered with that OEM as a developer to get special access to it. And frequently they only release SDKs for maybe their flagship device or a subset of devices. So you may not even always be able to get an SDK for the device you want. And it's even less likely that you're going to get the SDK for a specific version of that device. So if you want to try using these, there's 2 different options. If I'm going to make something in Android Studio that uses one of these classes, the first option is I can just create a stub class, and I can reverse engineer the class to grab all of the interesting methods that I want to use and grab their signatures, and just create a stub class that only has the signatures, no actual code. And I can specify it as a compile only dependency, so that when it's compiling the app, it will say, it basically treats it as if it was part of the Android SDK. And so that it will be like dynamically linked at runtime. And it won't actually include that in the body of the APK or the body of the DEX file. The second option is, it could be easier or harder depending on your experience, but it's more in line with how this would normally be done on the OEM side when they're actually developing their own apps to use these services, is you create a what's called an ADL file. And this is totally just, I just completely blanked out on what the acronym is. It's the Android something definition language interface. I think it's interface definition language. And it's basically a watered down version of the stub class that you'd create in a specific format. And it's a format that's used for specifying an IPC interface. And Android Studio will understand that and generate the stub class for you when you compile, and it recognizes that you're calling out to another process and that you don't have the body of that code. But either way, once you compile that app, you can plug in your device to your computer and click to run your test app on that device, and try using or messing around with these added this added framework code in a real application. The exception there being the dynamic analysis challenges I mentioned in the last presentation surrounding if they do require that the app is a specific user or that it has specific permissions, you may have a hard time without having a rooted device. Okay, looking at binaries and native libraries. For the most part, when you're looking at these, it's very similar to if you were reverse engineering a binary or library that was meant for a Linux device. So for the most part, just if you have an ELF binary or library, you can just load it into Ghidra or Binary Ninja or IDA, and it will work pretty much the same way. The only difference is there may be, is context basically. It's just if there is certain components that it uses on the device that may not exist on a normal Linux machine. So in the bottom here, I have some examples that you often see in malicious or vulnerable binaries. Things where they're using specific Android command line tools like the AM or PM command. The first one being the activity manager, and the second one being the package manager. So I mentioned that hostile downloaders can be pretty popular in pre-installed malware. So a lot of times you'll see cases where they just use PM install to install applications on the device. They can also do some fun things like there's flags where you can set the install refer, or I guess it's not the refer, it's not called the refer, but it's the application that sent the new application to be installed by the package manager. So I can say pm install -i com.android.settings, then a path to my APK file. And now from the package manager's point of view, the settings app is the app that is initiating this install. But in reality, it's whatever binary called the pm install command. But the settings app is going to get credit for that install now. You might also see some interesting methods of collusion or communicating between apps and binaries, or binaries and binaries, or framework code and binaries, framework code and apps, pretty much every possible combination. And a lot of times you might see some more traditional Linux methods being used, like just open sockets that are listening for connections from their colluding partner. I've also seen cases where if an app is running as a system user and the binary is also running as a system user, they will have access to the same SQLite database. And each app can put in information or pull out information as a means of communicating with each other. Another popular one is named pipes, which are kind of like sockets in a way, but basically allowing you to write and read to a file as kind of a first in, first out queue. Another popular thing you'll see added in this section is attempts to work around certain parts of the security model for Android. And so some places can be really good starting points for checking for modifications to AOSP. So things that are really privileged binaries like install-d, which is responsible for installing applications and setting up their SE Linux contexts. It's one of the most privileged processes on the device, or ADB. Things like that can be interesting places to look for backdoors. And in general, if you're confused about what the possibilities are for a binary or a script, looking at the SE Linux context can be a good place to start. It's kind of analogous to looking at the permissions for an application. It's what is possible for this binary to do before you even start looking at what it's trying to do. Just getting an idea, can give you a clue of, okay, based on what SE Linux context they're giving themselves, what might be the purpose of this, or what kind of functionality does it have? So here are some downloads that you can take a look at for the first two are downloads for the tools I mentioned, VDEX extractor, for converting VDEX files into normal DEX files. And the second one is the tool for converting Android system images to normal images, or to Linux images. Unfortunately, I cannot share any specific images from our resources with you. But if you want to take a look at the Pixel images, there's a link here where you can download the most recent updates for Pixel phones. And you can try doing these steps where you mount the system image or the vendor image and snooping around. And if you're really adventurous and you want to try looking at the Linux kernel, you can take a look at this Android Unpack boot image tool, which will extract the compressed kernel from the boot image. And I would say maybe don't try that unless you've already looked at a kernel before, or you've played around with the images, the system images, for a little while and gotten some familiarity with the Android framework, because the kernel is not easy to just load into Ghidra and start poking around. If you want to read a little bit further about some of these things, you can see all the public references for the platform APIs at this first link. Like I mentioned in the last presentation, some of the things that are available to system apps or to the rest of the framework code aren't included in this documentation. You actually have to go into the source code to look for places where it says @system API. But everything that's normal publicly available as part of AOSP to apps is included there. The second link is about writing ADL files. So if you want to try making an ADL file to, if you have a device that you know has some system modifications and you want to try using them, you can try using this to make your own test app. And the last one has a little bit more in-depth definition of each of the partitions that you'll see on a device, including a bunch that I didn't actually mention. So I want to start by asking if you have any questions, and then maybe I can give you a brief intro into the samples.
Thank you, Alec. So, all right, guys.
I posted a link to the samples in the chat. Alec, can you explain a little bit what's in the sample zip file?
Sorry, muted. Sure. So there are 3 samples in here, which I waited until after this presentation because I think they mostly include applications that work with other components on the device. So I wanted to give an overview of looking at the rest of the system image. I didn't include the whole system images here. I just included the individual parts that are relevant. But in one of these cases, I think it's called Digi or DigiTime. We have an OTA solution that was a third-party OTA solution used by a lot of different OEMs that turned out to have malicious code embedded into it. And it turned out to be really complicated. I don't know if I would necessarily recommend looking at this one first, but if you do look at it, you'll have a lot to play around with. In this particular one, you'll see that it has the actual DEX file doesn't look too suspicious. But when you look at the assets, there's these 2 files called license 1 and license 3. And they're not actually license files. To kind of help you get a start, I'll go ahead and tell you that they're actually compiled Lua code. And you'll see that there's an ELF file included in the APK as well. That's a Lua interpreter. And so this Lua code, it turns out, is this whole framework that can download other Lua modules and has access to system code through a Lua to, I think, like a Lua to Java interface, sort of. And it can download applications and launch applications and do all sorts of interesting things. In that same directory, I included all of the patches or all of the updates to that Lua code that I was able to scrape from their servers. So you can take a look and poke around at the different patches that they've tried installing on devices. And then the other APK, which I think is called temper.apk, is one of the examples of an application that they were downloading. And so you'll see that they were downloading all of these kind of sketchy applications that do different advertising and stuff. And those applications themselves were also downloading these jar plugins. And so I included 2 of the jars that I scraped from their servers as well. And so yeah, there's a lot to play around with there and see how it works. And it was a really interesting case because the OTA is one of the most, OTA stands for over the air. It's the system update application. It's one of the most privileged apps usually on the device. And so it's an interesting place to find malware. One of the other cases, I think, is a fake MediaTek app, which works. It's also doing some downloading and stuff, and it works with a fake men swap binary, which I've included there. And then actually I need to take a look because I'm not sure I remember what the third sample was. Give me 1 second. Oh, the third sample was a fake Google services application. I think this one can also get a little bit complicated, but essentially when it usually on pre-installed on devices that Google partners with, there's a kind of a big process that's like almost sort of like a microkernel. It's one big service for all of Google's apps, and also for Google services just on the device, like connecting your device to a Gmail account, things like that. And it's called GMS Core. And so this was, I think, kind of trying to pretend to be that process. It has a fake Google icon and everything, but it's actually an interesting case where they've obfuscated some code in their assets. And I think it's kind of a cool example of trying to retrieve the original dex file. So if you take a look, I've included I think the Deodex APK, and then also an ELF library that'll be necessary for figuring out how to decrypt the obfuscated dex file. And all three of these apps are, I think, run as the system user. So you can get a chance to see like some things that the system user can do that other apps normally can't do.
Thank you, Alec. More questions, folks? All right. So as we're a little ahead of schedule, would Vadim be able to start, say, in about 10 minutes? I know.
Absolutely.
Okay, great. So why don't we take a, thank you again, Alec, another great talk. So why don't we take a 10-minute break and reconvene at 1:45 Eastern. All right, excellent. Thanks again, Alec. And see you all in 10 minutes to listen to Vadim talk about obfuscation. Awesome, thanks. See you all in 10. So welcome back, everybody. And our next session is by Vadim Kotov, and he'll be talking about obfuscation in the context of Android. Over to you, Vadim.
Thank you. How's the audio and video? Can you hear and see the screen, folks?
It's sounding a little bit robotic again, but the screen is fine.
Can you at least
I can understand you. It's not ideal, but if it stays like that, we will be able to understand you.
Okay, let's try. Let me know, folks, if it becomes worse. Okay, so obfuscation is a really broad topic, and we'll only cover the Android aspect of it, only some of the popular obfuscation methods on Android. So obfuscation in software means transforming code or data such that it is difficult to understand, reverse engineer, detect, or modify. Sometimes people say that it's transforming the code so that it is semantically the same but syntactically different. This is another possible definition. I believe the original use case was protection of intellectual property. But of course, it can also be used for hiding malicious or fraudulent behavior from both reverse engineers and detection rules and antivirus scanners. It's also become a sort of a recreational activity. People just write obfuscated code for the sake of writing obfuscated code. An example with the International Obfuscated C Code Contest. And they have their official website, you can check out what they do. And of course, we know that there are many languages, programming languages, in which you can develop apps on Android. And but main sort of main two, I guess, would be the major two would be Java or Kotlin code, and native code, and the obfuscation can be applied at both levels. And of course, you're going to have obfuscated JavaScript code, obfuscated hybrid apps. It's really just the imagination is the limit here. We could roughly split obfuscation into sort of these broad categories: code obfuscation, as the name suggests, transforming executable code, and data obfuscation, and essentially transforming, encrypting, or compressing all of your data. The most popular ways malicious apps obfuscate themselves on Android are, when it comes to code obfuscation, layout obfuscation, API call obfuscation, and dynamic code loading. And for data obfuscation, it's typically string obfuscation. And we will cover all four of these techniques in this presentation. So let's start with layout. It's also referred to as name obfuscation. It's probably the basic, the simplest obfuscation technique. An obfuscator would simply rename, remove all the meaningful identifiers, class names, method names, field names, and so on. Examples include R8, or as it was formerly known, reprogard. It renames everything into just a single letter. Normally, when you freshly compile your Java project, class names, method names, all those things are packed into your dex. And by renaming them to just these shorter single letter names, or when you run out of those, you use double letter names, makes your dex just a little bit smaller. And so that's sort of another feature that R8 claims. Some other obfuscators, such as DexGuard, do the opposite. They make stuff bigger, and this screenshot right here shows what DexGuard does. It just renames everything into randomized sequences of uppercase I, 1, and lowercase l. And for any reasonably large class, it just all blurs together and becomes difficult to read. There is not an easy way to deal with this kind of obfuscation. It's the simplest, but it's somewhat efficient. Really is not much you can do besides just trying to rename things. Most of the time, manually probably would be the cleanest, most reliable way. You could try doing it automatically. For example, main variables after the methods that return values to them, something that JDEX does. But here are some rules when you are renaming things in a reverse engineering project. And they're good when dealing with layout obfuscation, but also generally good for any reverse engineering strategy for any platform. When you know what a method, a class, a variable is doing, then just name them accordingly. When you're not sure, don't be afraid to just what I do, I usually add this underscore maybe prefix, and so that I know that that's what I thought when I first saw it. And if you have absolutely no idea, for example, we're looking at a method and you see it performs a bunch of arithmetic that seemingly is incoherent, and you just can rename it into something, like do simple calculations or do complex calculations, something like that. And the idea here is when you rename stuff, you know that you looked at it. If these randomized names, you can really lose track of them. So as long as you rename them, they don't have to be perfect, they don't have to be meaningful. You can always sort of, for the first round, you can sort of just approximate everything and then concretize later when you do deeper analysis on other parts of the application. Another obfuscation technique is string obfuscation. It's also very, very common on Android. And the idea is very simple. Let's say you have a method that takes a string. In this case, it's a constructor for the URL class. And it takes a string as an argument. You transform the string, in this case, it's just encoded in base64, and you wrap this string into an accessor method. And the accessor method simply deobfuscates, decodes the string before it is passed to the constructor. Very simple, but very efficient. You see, stuff like URLs, for example, is very useful when you're writing detection rules or antivirus signatures. A URL of a command and control server for a malicious app is really nice and reliable artifact by which you could efficiently detect that malware. So obfuscating the strings helps malware folks to evade these rules and these detections. And this is a toy example, right? We only use base64, but really you can use anything. You can apply any kind of encryption. In fact, we'll take a look at such a sample. Any kind of transformations, any kind of encryptions. And what makes it efficient is that for malware folks, it's really easy to just change the encryption key, for example, and re-release the malware if the antivirus signature had been updated, for example. So that's string obfuscation. And string obfuscation is you actually can do something in this case. You can use scripting and various analysis tools to make your life easier. When you have an obfuscated APK and you would like to understand what it does, if you like to reverse engineer it, it would be good to first deobfuscate all the strings. And commercial tools typically provide you with APIs and scripting APIs, like a Python API, for example, that you can take advantage of, and they give you access to the decompiled code, and you can transform the strings back. For example, one commercial decompiler is called JEB, J-E-B, that allows to do that. When using open source tools such as JADX, you still can do it. You just need to take a couple extra steps. And we're going to explore what can be done in this with the open source tools. Now, as you know, it's fairly trivial. You can use APK tool. It's fairly trivial to decode an APK and extract and get access to the Smalley files. Each class in an APK has a corresponding Smalley file, and Smalley is an assembly language for Dalvik. So when you have these files, you can go over them. You can find the assembly code responsible for calling the accessor method and passing the obfuscated strings to that accessor method, then you can either use grep or write a Python script that goes over the Smiley files and extracts these strings. And let's see. Let me show you one quick example. Let me stop presenting for a second. A useful tool to just quickly try and deobfuscate some strings is CyberChef, developed by GCHQ. And it is a very nice interface. We're going to look at this example here. We opened an APK in JDEX. The APK will be shared with you. I already navigated to the app class right here. And here are the methods. I'm sorry, here's the accessor method that deobfuscate strings before passing them to the actual method that is using the strings. So we'd like to know what is the real value of this string, for example. Let's paste it in CyberChef. And let's follow the deobfuscator method. Go to declaration. Okay, so we can see that calls yet another method. We can go to declaration and see that method, first what it does, it removes the URL encoding. URL decoder .decode. Great, let's add that. This on the left, these are a list of transformations that you can apply to your inputs, and the output will appear here. And this is the recipe. This is the stuff. This is a sequence of transformation that the input string goes through. So we can simply drag this right here. And now we can see that after removing a URL encoding its base 64 string, we can just do that. And we can see that it's gibberish, which means that we're not there yet. There's something else. Let's continue. So here's an example of good renaming strategy, for example. It's what JDEX does automatically. It checks that, okay, this variable, whatever originally named, and they just rename it to decode. And it could have done better, but it's just a neat idea. This is just one example of what I meant when I talked about renaming. So we got this decoded value. It is passed to the base 64 decode wrapper, and we can go to declaration and make sure that indeed that is the decode wrapper. And it removes the base 64 encoding. And now, like below, we can see that it calls this function first and passes the second argument. If we trace back the second argument, we will notice that it's this global variable key that's passed to it. So that's our decryption key. Here we can see that an instance of a cipher being created, and we can see that it's an AES cipher in a single node with this particular padding. The cipher in the node is what's important in CyberChef. CyberChef takes care of padding automatically, so we don't need to concern yourself with it. So let's look for AES. It's a nice search bar. So we get AES decrypt. and we need to populate all these fields. Well, first of all, let's continue. Let's finish analyzing our code. So this is the secret key spec. Let's actually rename this. It's right here. What it does, it takes this big key value and it creates a byte array of size 16 and puts first 16 bytes in there. So we know that key should be first 16 bytes of this string. Let's just do that. Let's just get the first 16 bytes and paste them back here. That's the key. Notice that by default it expects it to be in hex, but we're pasting just a regular UTF-8. So I did that. Let's continue. It's very strange. For some reason, can't rename a variable, but we at least can name this method. This is a good artifact, and you might have it too. Just need to expand it a little bit. Let's call it get key. And then it initializes the cipher. It passes it the key. The first argument is letter 2, which means that 2 stands for decryption. If it was 1, it means that it would initialize the cipher for encryption. So in this case, it's decryption. So it passes the key, the key specification, and passes the initialization vector. The ID. We just copy the ID and paste it here. And again, it's not hex, it's UTF-8. Another thing to notice is that the input also expects, here we go, that decrypts into SHA. So what if you have multiple strings? Let's go back to our app class and check out this string, for example. It's a big string, interesting what it decodes into. Just put it here, and of course it can't decrypt it because it treats these two as one string, and so it becomes skewed a little bit. To avoid that, there's a nice operation called fork, and fork splits these things by line, and then processes these strings separately. And as you can see, that is actually some ID. It didn't provide us any information. Let's check out this string. Key hash. In fact, we can go see find usage on the Deobfuscation method, and that will reveal us every single place in an app that calls on, and as you can see, there's quite a lot. It's quite a lot here, 100 entries here, 1,077 total. And what these did in this app, they distributed everything. Maybe not everything, but most strings, even the legitimate strings, they obfuscated. Why did they do that? I expect the ones to just get stuck, get bogged down, analyzing all those strings. And that is another challenge. There's really not much you can do except for reverse engineer all those deobfuscate all those strings, and just try to make artifacts of malicious behavior. So this is how you do really quick deobfuscation in using CyberChef. Okay, but that's not perfect. you still, in cases like this, you still want to have just a clean APK to analyze it, focus on the behavior, not bother encrypted strings. And to do that, we can use APK tool. Now, APK tool not only allows you to decode an APK, so you build and compile it back to an original APK. I'm sorry, to a new APK. So the idea is fairly straightforward. You decode the APK, you examine your accessor method that performs string deobfuscation. In this example, you can see, let's open it in JS and just go through this example. It's the yesterday's store fraud app, by the way. As you remember, I mentioned that the version we shared yesterday was deobfuscated, and this is how we did it. Let's go to an obfuscated, find an obfuscated method, handler, or pager, for example. API, okay, let's get here. So, a bunch of obfuscated code here, and the accessor method is called decrypt. Let's look at the Smalley and find what this code looks like in Smalley. Here we go. How we find how it looks like in Smalley. Let's get back to the presentation. So we have these three small instructions. Const string simply puts a string into a register v1. Invokes static invokes a static method. In this case, a decryptor, the accessor method is a static method, and puts the result into v1. The move result object moves the result into v1. And, the argument is in v1, and then it moves the result into back into v1. And if we deobfuscate the string, it's actually deobfuscated to X requested with, and in these two lines, you'll notice that after this code on the top ended executed, and after this code on the bottom ended execution, the program state is the same. This one ends with v1 containing a deobfuscated string, and this one ends up in v1 containing the obfuscated string. But it removes all this the obfuscated stuff that's making it close to the clean original Smiley that was prior to that was before the obfuscation. And so we do that for all the small, then we build it back. One remark here is APK tool has this command D, which stands for decode, that decodes the project. And it is beneficial most of the time to pass the -R flag. It's not necessary for decoding, and what it does, it just skips decoding the resources. I've had multiple times issues rebuilding the resources afterwards. So skipping that, we're not interested in resources most of the time. Most of the time, the obfuscation lives in smaller code. So just pass the R flag, and it should be fine. And so to deobfuscate the thing, I wrote a very crude script specifically for this sample, just to illustrate how can you, just to illustrate a kind of type of script you might need to quickly throw together to deobfuscate a sample. It's by no means an example of amazing programming. What it does, it goes over, you pass it a path to the Smalley folder, the decoded Smalley files. It will simply go file by file and it will throw a trial at this class, smiley matcher, which is essentially a glorified finite automaton that searches for the sequence, the exact sequence we've just talked. It extracts the obfuscated string using the regular expression, passes it to the deobfuscation method right here, the deobfuscation function. Actually, let me go back here real quick. Let's get to the decrypt method and go to declaration. As you can see, it's almost exactly the same. It's just a Python re-implementation of the deobfuscation method. And it performs the replacement, this replacement I've just mentioned, and writes everything back to the smiley. Using these sort of finite state machines is a good way to implement pattern matching on all sorts of. This script is included into the archive that we will share, so you can explore it in your own time. I just wanted to mention briefly how it works. And so let me show you what you do in this case. So this is our file, and this is our APK. We call APK to decode it, and I'm sorry, T, and don't forget the R flag, and don't forget the extension. Okay, so we have this folder here with the decoded stuff. Let's just for out of caution, let's make a copy of this folder. And now let's call the deobfuscation script. It also additionally prints out all the deobfuscated strings, just to get an idea what are some of the hidden strings, and we can see the malicious URLs here. We use APK to B, and we pass it a flag O to specify the output file. It's called clean APK, and we point it at our deobfuscated folder, and it will assemble it back. Hopefully it doesn't fail. Yeah, it seems like it did. Great. Now let's open it and take a look at the same class we just saw. Where's it down? Here we go. Everything's clean. And most things are clean. Sometimes you have this sort of chain, it's sort of a chain case where it first passed to some other method, and then in that method, it only decrypted later in that method. But it's just a few instances. Most strings are deobfuscated, and we can just proceed with the analysis. Let's say you would like to. Let's say you're not satisfied with the static analysis, and you would like to perform some dynamic analysis. We maybe want to run it and debug it, maybe hook some functions. You want to run this new sample, the clean sample that you've compiled in an emulator or on a real device. After you've built it out, it won't run because Android will only run signed apps. And this slide right here shows how to sort of self-sign your app so that Android can execute it. I'm not going to go into details. It just comes to knowing these commands, creating a key. First, you need to create your key pair, the RSA key pair, and then you need to sign your APK. It's as simple as that. we covered that. Okay. And sadly, string obfuscation is the only, probably the only obfuscation method where you can genuinely do something, you can genuinely fix an APK and make it better in a fairly trivial and fairly straightforward manner. Other types of obfuscation are also relatively simple to implement as a reverse engineer. One of the obfuscation is obfuscating API calls using reflection. So this is a trusty old example that we've used many times right now, just getting sim operator, 2 lines of code, instantiating a telephony manager and calling a method, get sim operator, which returns a string. That's one way, that's the straightforward way to call it. But you can also call it using reflection. So let's say you have your telephony manager, you instantiated your telephony manager, and what you do is the telephony manager, the class has a field called class, which gives you an object of class. Java is an object-oriented language, so everything is a class, even class itself. And from there, you can call a method called getDeclaredMethod, which returns you a method, literally an object of class method, called getSimOperator. And then on that object, you can call a method invoke, pass it to your telephony manager, and it will return the operator string. Sorry. What's the difference here? The difference is that this is a bit more verbose, but this now all of a sudden becomes a string, which means that we can obfuscate it using string obfuscation. And of course, methods that are being called by an APK are also one of the indicators as both analysts may use to just get a quick idea of what an application can do, and antivirus signatures also use to describe malicious behavior. And when you obfuscate it, it of course becomes obscured now and hidden from view and requires extra work to understand the code. Finally, and there's no slide called dealing with API call obfuscation because there's not really much you can do. I mean, I'm sure you could recode all that back into the snippet above, but it really becomes cumbersome and probably not worth the effort. As long as if you see these kind of strings are obfuscated, as long as you deobfuscate them using the technique shown above, shown earlier, it's fairly accessible. It's maybe just a little bit more verbose. Finally, dynamic code loading. It's another broad topic. There are many ways to, well, first of all, what is dynamic code loading? It's just loading an executable code which is not initially present in the app. So as you know, you have your classes dex, the entry point to your app lives there, and you launch the app, some piece of code is executed. But you can also have another dex file, where some additional dex that you can load later. Or you can download that dex from a server and download later. Load into the context of your app. To do that, you can use one of these classes, dex class loader, path class loader, or dex file. Dex file is deprecated in API level 26. There are way more loaders than these, but these are the most commonly used. There are also ways to manipulate lower level structures of the Android runtime and avoid calling these functions altogether, but for the interest of time, we won't cover those. And so these are common types of DCL. One is just using dex class loader to load the original dexes or jars or even APKs. Another one is the custom JavaScript interface, something that we looked at during Toll Thread and Hybrid Apps session. You can extend your JavaScript interface to be able to call Android API methods, and now your JavaScript becomes as powerful as just regular Java code. And you can load JavaScripts that perform malicious activity from the command and control server. I wouldn't say it's widespread, but comes up pretty often, this technique. And you can also use native code, of course. Native code DCL is not Android specific. You can always read some executable code from the binary, allocate some memory, and mark it executable, put your executable code there, and just call it. It's really a very, very broad topic, and so we're not going to cover it as well. Let's talk about the DEX class loader. DEX class loader simply loads an additional DEX. You instantiate it by calling one of its constructors, and the constructor gets a path to the jar or SDK, jar or APK, and that's the required argument. It takes 4 arguments, only 2 of which are required. And the second required argument is the parent class loader, which you can instantiate by calling get class loader from context. So that instantiates a DEX class loader specific to the path that you've provided. And then you call load class to load the entry point in the DEX, and that returns a class object. And then you find the entry method, the entry point, the method that you'd like to execute in your DEX, and that returns a method. And you call invoke a method. This is essentially the reflection that we've just covered. And this kind of DCL is very widespread amongst malicious apps. They would download a malicious DEX or jar or APK with malicious payload from the command and control server, or maybe hide it encrypted in assets or elsewhere, maybe hidden in some image using steganography. It's really, again, a multitude of ways to hide a payload or download it. And then they dynamically load it using this technique right here. And I think that's all. That's the theory part. The samples that we shared. Let's see.
I haven't actually shared the samples yet. I'll paste the link.
Awesome. Thank you. I just quickly go over those. So you get this this app right here, which we looked at, is a Toll Thread app from yesterday, which we deobfuscated and recompiled. Then the script used to decompile it, and a couple additional samples. This one is a sample we started analyzing using CyberChef, and this is just another sample that's using a combination of techniques that we covered. Also, also one of the Toll Thread funding. So this, I think, you could try analyzing them during a hands-on session, and right now I'll be happy to answer questions. Any questions?
Thank you for the presentation, buddy.
Again, Sebastian's also shared some of the obfuscation files. So obfuscation samples, sorry. So questions, guys?
Yeah, this is a really important and interesting topic because, well, any non-trivial malware these days just uses some kind of obfuscation, most likely. And so coming up with ideas of how to beat obfuscation at scale is really important, because otherwise you're just gonna classify the obfuscation algorithms with your whatever methodologies you're using to find bad behavior. So it's a big research field, I think.
Yeah.
Could you go into some detail about what how Google actually goes about finding obfuscation at scale? Because the techniques that we discussed today seem pretty hard to do at scale, at least the patterns.
Honestly, this is one of those things that I don't want to talk about too much in a recorded session. It's very rare. It's like the first time I say that, but we put in some work and we have some very nice results. Visit us one day, then I'll show you some stuff in person.
I have a question.
Fair enough.
Yeah, I think, I mean, this is really insightful. For us, we're also trying to do some research about the obfuscation on the Android malware. Currently, my question is, I mean, we know that there are a lot of, I mean, obfuscation techniques available there. And today, maybe you just introduced some of them. So do you have any, I mean, intuition, like which kind of obfuscation is the strongest one, or which is the weakest one, something like that? Because, you know, we can also apply different combination of the obfuscation skills on the Android malware APK, but still keeps the original malware, still keeps the malware behavior, right? Malicious behavior. So do you have any insights? So, I mean, which are the most common one and the strongest one to bypass to evade the check of the antivirus engine?
Right. So it's a really deep question. In general, what's in this sort of security industry broadly, the strongest kind of obfuscation is considered to be virtual machine obfuscation. Is where you create some custom virtual machine, some custom instruction set, and then you transpile your code into that bytecode and apply, and essentially your program becomes an interpreter. And that is the hardest one, because if you want to genuinely completely reverse engineer it, you have to first reverse engineer the bytecode, the virtual machine, and then get to the actual contents, the actual meaningful code, the meaningful malicious code. But even outside the sort of the extreme techniques such as virtual machines, something like hybrid apps that you covered are often very difficult. They're often actually very close to this VM obfuscation idea, because you can create an obfuscated JavaScript interface, then load some obfuscated JavaScript in there. And then outside of obfuscation, there are just some kinds of apps or kinds of architectures that are almost as difficult as if they were obfuscated. One example is .NET apps on Android. You can develop .NET apps. Your app will live in mostly a dynamic link libraries, PE, which is Windows format, and there aren't really good tools to extract the original code. Furthermore, there are versions of this that transpile everything into native code. And so that now you have something that was written probably in C#, then that was translated to, if I forget, the .NET a .NET bytecode, and then that was transpiled into native code, and that is better than any obfuscation in my opinion. So, and to that question, there are also two additional remarks I would like to add. One is malware folks operate as sort of this underground business, and they try to roughly stay rational in that they try to do the minimal effort needed to evade detection and complicate the analysis. So luckily for us, it's not often that we see some extreme kind of obfuscation. And they don't need to put that effort because as long as weak obfuscation works, they just go with it. The second observation that I would make is the more complex your obfuscation algorithm, the greater is the chance that that obfuscation will break actual functionality of an application, because obfuscators do some low-level stuff. And if an obfuscation algorithm is not well thought through, then in some complex cases, they might actually break the actual functionality of the actual behavior of the or actual algorithm that you're trying to obfuscate. So that's another reason sometimes people would forego really complex obfuscation and favor easy ones, as long as it can help them evade antivirus signatures and simply complicate the analysis. That's my answer.
Thank you, Vadim. More questions?
Hi. I have one question. Regarding the dead class loader, which seems commonly used by Malware, I'm wondering how the legitimate apps would use this function and why they are unreplaceable.
There are two reasons I'm aware of. Thank you. There are two reasons I'm aware of. One is that DEX format actually supports up to, I think, 65,000 something method and field names. So if your app is very large, it will have more methods and fields than that. So you need to spread your code amongst multiple DEX files, and you need to dynamically load them. And I think until some version, I don't remember right now. I think API. I don't remember right now, but at some point you have to use DEX class loader to deal with that. Second reason is that it allows you to you can have multiple DEX files, multiple small DEX files, and minimize your memory footprint. This is with low memory. That's another use case. And finally, dynamic code loading is used in some markets and distributions platform as just the major way of shipping a product. It allows you to hot swap executable code, hotfix vulnerabilities, or quickly release patches without making a user re-download the full APK. This, however, this last thing, however, is not allowed in Play. Play apps can only update through Play Market. I hope that answers your question.
Yeah, sure. Thank you.
Thank you.
Thanks, Vadim. More questions?
I have another question. So just now you mentioned maybe for different obfuscation techniques, the developers they need to pay different efforts, right? So how do you define the effort here? Do we say that maybe API reflection pays much more efforts than the screen obfuscation? So maybe just now, I mean, the developers just using some third-party libraries to just obfuscate their code and then just release it, right? So how do you define the effort?
I think what you've said is a fairly good heuristic to define the effort. Is something using a commercial obfuscator is probably low, or open source or commercial obfuscator is probably low effort. Although commercial obfuscator usually are paid, so it's not a question of effort, but a question of money, or a question of investing resources into your malware. At the algorithmic level, if you were to define which obfuscation algorithms takes more effort, is everything that is just, in my opinion, it relates to the complexity theory. Literally, the more complex is the transfer, the more careful must you be implementing it so that you don't break the actual functionality of an app. To calculate that exists. It's only really just basic heuristics. In other words, if you doing a trivial transformation in a smaller file, that's probably a relatively small effort. If you're transpiling small into your custom bytecode, that's a lot of effort, because transpiling is generally a difficult difficult thing to implement properly. Right? Well, do you know what one instruction does? Are you sure that you are mindful of the flags that it explicitly sets, or the other changes to the program state that it might be making implicitly? Yeah, that's about it, I think.
Great. Thank you, Vadim. So I think we will end the session now. And as it's now, again, very insightful presentation on a super important and growing problem. So I think it's now 2:39 Eastern, and what I would suggest is let's come back at 3:40 p.m., 1 hour from now, with a slightly early lunch break. And then we will just chug along with the next talk by Vadim also, followed by 2 talks by Roman. Is that okay for you, Vadim, to start 4 Eastern?
Yep.
And hopefully, the slightly adjusted schedule will work for Roman as well, assuming we stay at this schedule for the next few hours. So, okay, guys, everybody have a good lunch, and see you soon. See you in an hour.
Thanks, folks.
Welcome back, everyone. For those of you who joined late, Bill was giving a quick tour of Dartmouth propaganda material, telling you, what a great place we are, and showing you some great pictures and videos. But it's time to move on to Vadim, who's going to be talking about hacking and unpacking. So over to you, Vadim.
Hey folks, I'm trying a different microphone. Is the audio quality any better?
Much better.
Much better.
Okay. Yeah, I'm having weird connection drops from time to time. I'm not sure what the reason is, but if it drops, I will connect through my phone, and hopefully I'll be able to finish it anyway. Okay, so packers on Android, just like with obfuscation, will only cover basics and only cover Android specific stuff. For the topic is really, really broad, and the whole course could be dedicated to packing alone. What is packing, first of all? Packing is a process of compressing and potentially encrypting the code of a program. The original code is then replaced with the decompression routine, the entry point to your app is replaced to the decompression entry point. When it is executed, it unpacks the original code and executes it. It transfers control to it. And the original idea for packers was that when the memory was really expensive, packers were used to just conserve memory during both storage and transfer. Memory is relatively affordable these days, and so packing is used not so much for compression, although that also is the case, especially for IoT devices, but for desktop computers and modern smartphones, it's more of another adversarial technique that is used for both IP protection and detection evasion and complicating reverse engineering. Common features of packers include obfuscation. If you packed your code, you might as well want to obfuscate the unpacking routine so that it is even harder to reverse engineer. Anti-analysis techniques are very common. Virtual machine and emulator detection, anti-debugging, and hooks removal. All those exist to make it harder to debug a packed application as well as analyze it dynamically. And most packers, I think it's fair to say that most packers on Android, at least the commercial ones, use native code for unpacking. They would have an SO, a native library on board, where this unpacking code is implemented. And there are multiple reasons for that. One is you have a low-level access to such thing as multi-threading. You can use low-level tricks for debugging evasion and emulator detection and so on and so forth. So generally, it's a good idea if you want to put some analysis protection into your application to have them implemented in the native code as opposed to Java code, as is just there. Have a bit wider reach to the low-level components of the operating system and of Android runtime. This diagram shows a very abstracted process of packing. So here on the left, you have your original APK, and as you know, your code resides in classes DEX or multiple classes DEX, if it's a multi-DEX APK. And then there are various resources, and that includes the manifest, all the interface information about the interfaces you're using, the widgets you're using, images, whatever. It's just a blanket term for everything. When you throw a packer at it, it will take the original classes DEX, it will compress it, it will possibly encrypt it. In fact, almost always the case that it's also encrypted in addition to compression, and then put it somewhere in the packed APK. And then it will add its own classes DEX with its own entry point, which when you launch an app, it will access this encrypted piece and apply this in reverse, decrypt and decompress, and transfer control to it. And in fact, we covered dynamic code loading in the previous session. Is typically how it is done. Using it unpacks the classes DEX and uses DEX class loader to load it in memory and make the application context aware of it. Okay, so just like with any problem in reverse engineering space, you can approach it statically and you can approach it dynamically. The static unpacking implies fully reverse engineering a packer, understanding how it works, and based on that knowledge, writing an unpacking program. The advantages of this approach is that it is reliable and easily automatable. You have a robust deterministic algorithm implemented in either script or a standalone executable that eats up APKs and dumps or outputs the original unpacked classes DEX. And you can efficiently automate that, throw it at a large amount of packed APKs, and just crunch them really efficiently. And that's probably its main advantage, the scale and reliability, scalability and reliability. The disadvantage, of course, is it is very cumbersome to analyze a packer. They really go out of the way to make it as hard as possible. And it's not only due to obfuscation and anti-analysis tricks. They are very efficient and they waste a lot of your time. But a lot of the code is just written in a deliberately complicated way. For example, one commercial packer, first thing it does, it is tries to read classes DEX from the APK and parse it. But it performs the read operation. It reads the file byte by byte. So if you were to, for example, execute it and analyze how often does it, analyze file read operations in hopes that that will bring you to give you some insights about the unpacking, you'll see thousands of file read operations. And what you do with those, it's an overwhelming amount. So all those little things just to waste reverse engineers' time, not necessarily obfuscation alone is the problem. And also constant maintenance is required for static unpackers. Oftentimes when a new version of a packer comes out, they change their algorithms. Even little change will require you to update your static unpacker, and changes might be quite significant. And at times, you might just have to start from scratch, essentially reverse engineer the whole thing again, because the changes might be so dramatic. The dynamic unpacking is the opposite of that in a sense. The idea is that you let it run in a virtual machine or on a real device, and in a control environment. Then you let it unpack itself, because obviously every packed program has to unpack itself at some point. And you just copy the unpacked code at that point. The advantage of this approach is that it is much faster than reverse engineering. It really takes maybe a couple minutes. And it's also agnostic of packers' inner workings and version variations. You just throw a bunch of packers at it. It will work for some, it will fail for others, but for those that it works great. The disadvantage is it is difficult to automate. And what I mean by that is there are two actually reasons why it is difficult to automate. One is anti-analysis tricks, of course. Let's say you fire it up in a VM and it has cloaking. It has VM detection code. Or you fire it up on a real device and it turns out that it will fingerprint the device and analyze and determine that it's a test device, as was covered during the cloaking session. So that is a problem. And another problem, when we run, if you want to run a dynamic unpacking code cleanly, you will have to do the following steps. You restore the snapshot of your virtual machine. You run your unpacking code, you then suspend your virtual machine, and then you analyze the results. And that takes a lot of time. And when you analyze hundreds of thousands of APKs, that time accumulates. And this is very, very inefficient. What if packers detect virtual machines? Now you can only run it on a real device, which is even harder. After you've ran, let's say 3 or 4 or 5, whatever, 10 malware samples, for example, on your test devices, is your test device usable after that? Well, you probably have to re-image this at some point. So one way or another, it wastes a lot of time. So automation is really, really big problem with dynamic unpacking. And in addition to that, some packers are actually well aware of researchers' attempts to quickly sort of dynamically dump them, and instead dump the original DEX, and instead of And what they do, they unpack original DEX in parts. So at no point there is a full original DEX in memory. And so now you have to actually reverse engineer it at least a little bit to at least know where do you grab those pieces and in what order and in what area of memory. So the general rule, or at least that I follow, is that if a packer is really, really complex and it is possible to dump it dynamically, dump the original code dynamically, and it's not very prevalent, then I would go with dynamic unpacking. For something that is really widespread, whose versions, for example, change relatively, they're relatively rare to change, then maybe it's worth investing into writing a static unpacking. But it's really, you really have to balance here. You really have to weigh exactly what kind of issue you're dealing with. Is it a popular packer? Is it just a few one-off case? At the end of the day, becomes quite a complicated question. There are generations of Android packers, and there is no agreement. There's not a central authority that assigns generations. But this three and a half that I will show, I think is pretty safe. I think most researchers would agree on those, and they differ in the way they unpack the original DEX. I also added another column here called how to unpack dynamically. Why am I talking about dynamic unpacking and not static is because there's really not much to talk about when it comes to static unpacking. You just have to reverse engineer it. But dynamic unpacking is where the sort of is a good proxy for complexity, evaluating complexity of these techniques. So the first generation Android packer, they unpack the original DEX to the file system. It's the simplest way to do that. Read the compressed and encrypted original DEX, unpack it, write it somewhere into some file. It's very easy to unpack dynamically. You just wait for this file to appear and you just copy it from your device or from your VM back to your computer. The second generation packer unpacks original DEX into memory. Now, the original DEX never touches the file system. So you need to know where in the memory the original DEX resides and then scrape it from there using a memory scanner. It's a bit harder than the first one, but still fairly straightforward. And the 3 and 3+ generations are really problematic ones. The third one also unpacks the original DEX into memory, but they do that. They load separate classes upon loading. Now, if you want to dump the original DEX from memory, you'll have to make sure that all relevant classes are loaded. So now you actually need to know a little bit about package inner workings. The generation 3+ is essentially the same, except the original classes are decoded upon execution. So now not only you need to know when they're loaded, but when the relevant code is executed. And depending on the application workflow, some parts of code might never get executed. If you remember from yesterday's toll fraud session, a toll fraud app might check your SIM operator, and if the operator is not supported, they won't execute. Therefore, the classes responsible for executing malicious code will never be loaded. So now, in addition to the packer, you have a bunch of potential conditional statements that prevent the malicious payload from execution. So these are 3 generations of Android packers. Some would name fourth and fifth generations, and those have to do with custom bytecode and virtual machine protections. But this is where the line between packing and obfuscation becomes really, really blurred. So I think these three is a fairly safe classification. Okay, so Frida is a tool commonly used to deal with packed apps. It is a dynamic instrumentation framework for Python. And by instrumentation, I mean it essentially can control an application in question as a puppeteer. Its features include, it supports pretty much any popular platform and executable type, be it Windows, Linux executables, Mac executables, Android or iOS programs. I guess it's fair to say that its main mode of operations is hooking API functions, both custom and something like system APIs or library functions. And by hooking, I mean intercepting and possibly altering the functionality of the functions, the body of the functions. It has the ability to read and write memory and a lot of convenience functions that go with that. For example, pattern matching for memory scanning and so on, and allows you dumping areas of memory, and which is especially useful for second and third generation packers, where you really that's your only option to scan the memory. And the overall is a Python library, and you sort of set up your Frida script in Python, but the injected code is written in JavaScript. Let me stop presenting for a second. The official website is frida.re. It has documentations, it has examples. It has good API reference, so it essentially has a catalog of all the functions and of all these convenience functions it provides, but maybe it does not have its Android section is not that comprehensive. But in the end of this presentation, I put some links into really nice tutorials that you can read in your own time and get a specific Android-related information about Frida, and also a lot of stuff that a lot of modes of operation that work on Android. It would also work on iOS, for example. So to set up Frida, you need to install the Python library. It's called Frida-tools. It's both Python 2 and Python 3 are supported. I use Python 3 because Python 2 was deprecated in January this year, I think, or last year it was. I think last year. And then you should go to the official GitHub and download the server binary. And I'll tell you why you need it in a minute. Then you need to launch your virtual machine or connect your device via USB. And then you need to copy the Frida server to that device. The server sits there and communicates with your host operating system or your host script, and receives commands and actually interacts with the target application on the device. And so the reason you need a Frida server is just this agent that sits on the device and communicates with your script and your host using ADB, which is an Android debug bridge that you've already covered, I believe. And so that's the basic mode of operation. That's how you instrument Android apps using Frida. So this snippet here shows a sequence of commands you need to issue to load your Frida server binary to your device. It's ADB push. then your file, your local file, and then the folder on your remote device. Data local TMP is a good, typically where people put those. It's a temp folder. Basically, you can put anything in there. It's writable. Then you call the shell. In this case, I'm using an emulator. You can become a super user, and don't forget to give the executable privilege to the Frida server. It won't have it by default, and you just run it as a regular Linux binary, and it will be spinning there and talking to your Frida host. So let's just quickly do an example. Here's the test app. This app will be shared with you in the archive. It's a very simple app. All it has is this text field that's called myTextView, and it has this method called displayText. It takes a string as an argument and displays that text in on the app. And when the first thing that this program does, it calls it and passes a string hello Android. That's what we see. So I've got it here, and let's run it. By running it in Android Studio, it will automatically launch your virtual machine. You can, if you don't want to run a particular application, you can execute your, you can launch your virtual machine through AVD Manager. It's this little icon right here. I hope you can see it. Here it goes. It just says hello Android. It's very simple toy program. One remark: you might click on AVD Manager and you can see this is an entry that corresponds to that emulator, to that VM. You might find nothing in there, and that's because you need to download an image. But it is very easy to do. You just click on Create Virtual Device, select your device. Mine is Pixel 2, and it will download it automatically. So it's very straightforward. But back to our example. So, hello Android. Now, let's walk through this Frida script. As you can see, well, first thing we need to do is to import Frida, and then here's a script. First, we need to get a handle to the device, and to do that, we call get USB device function, and it will be the same for your VM. It will be sort of a virtual USB device, and it will be the same for the actual device connected through USB, most of the time at least. Then you can call the device spawn function to launch your app. In this case, the name of the app is com.example.freedatest. That returns a PID, a process ID, and then you attach to that process ID and create a session. You don't have to spawn an app. You can attach to app that is already running. In this case, you call attach, and you just give it an app name instead of the process ID. So this is then the next goes our JavaScript code that will be executed in the context of the target app. So the first line here is console log. It's a simple logging. It will output this into the command line. If you want logging for your script, for your instrumentation script, console log is how you do it. All your interactions that you'd like, all the instrumentation code that you like to be performed in your script should be passed to as an argument to a function JavaPerform. JavaPerform takes one argument and it's a function. That whole thing right here is a function that is defined in place and passed as an argument to the platform, to the perform method. It's defining functions in place right here is a common thing in JavaScript. To my taste, it's quite unusual, but if you read a little bit on JavaScript, you get used to that real quick, if that's unusual for you as well as for me. Java is essentially a handle to a bunch of Java helper functions that Frida provides, and a full list of those helper functions can be found on the official website, and also the links that will be in the end of the presentation. Also, the tutorials there also cover that extensively. So we're not going to go into too much detail here. All you need to know is Java is a handle that is available to you to access Java-related helper functions. Use method allows you to get a handle to a particular class. In this case, this is our full class path. There's a main activity. That's our class. That's our application name. We access it through the full path. And then what we will do is we will hook our function display text. And it is very easy. You have a handle to my activity. You can access the handle to display text method through that main activity. And you can access its property called implementation, to which you pass a function. That's another function sort of defined in place. And that function will do or will be executed in place of the original display text. Sometimes you want to do something. In fact, most often you want to do something to the hooked function and then still call the original one. And you do that by calling it through this handle. This will call the original method with string hello Frida. And hopefully when we execute it, instead of hello Android, we will see hello Frida. Let me go back. Okay, let's see. Hello Frida. So we hooked the function. One important detail that I forgot to mention, that once you spawn this app right here, it executes a new process, and that new process is in the paused state, which means it is not executing. And it is really important because that allows you to execute the hooking code as early as possible, even before on create. Okay, so this JavaScript code is just a string. We pass that string to create script function that is accessed through session. And that is a script object. And we call load on that script object, and that loads our script in the app. So from that point, our script is right there. It is executed. Now we need to let our application run and perform this, and we'll see the effect of the hooking. Another important piece, another important remark here is that notice there's this input function. It's a Python function. What it does, it just reads the input from the command line, from the console. Having it like this will be equivalent to something like a press any key to continue. And it is here because we need to pause the Python execution after we've done our injection and resume the process. If it's not there, it will just go to the session detach. It will detach, and it will halt. The program will terminate, and the script will not have any time to complete, and you will not see any effects of your hooking. So always have this little input thingy or any other sort of delay in here to give your script time to actually do what you want it to do. So now let's take a look at let's execute that script. It will be hang on. It will be shared with you. It's called Android Pie. Pretty much its whole contents are on that slide. We will execute it, but before that, let me check if we are running our Frida server. I've already copied it. Simply ADB shell allows you to get a shell on your device. So now we're actually in our device, and my ADB is configured to be root by default, so I don't execute SU or anything like that. So I'm already a root. We will do, what is it, data local TMP Frida server. So we'll launch Frida server. Let's go back to our code here. If you want to test, let's say you've just installed Frida and launched Frida server. If you want to test if it works, if your host can communicate with the device, if Frida can communicate with the device, you can call one of the convenience programs called Frida PS. Frida PS is just simply, it's an equivalent of PS function to just list the processes that are running, and the flag U, I believe it just limits it to user processes. And sure enough, it works. It shows us all of the processes that are running on our device right now, and then maybe even our Frida test. But we will close our Frida test for now, because our script spawns it automatically. It doesn't need to be open, and we will run this script, hello Android Pie. So, and as you can see, instead of hello Android, it shows hello Frida. That's exactly what we told it to do. And as you can see, it outputs stat. Where the stat come from? It's from this, so this logging message. This is a very simple example. It's a toy example, but any complex Frida script will be using this basic functionality most of the time. Of course, Frida has a bunch of convenience methods that allows you to handle a lot of typical situations. Now, for example, it allows you to, instead of just executing the script, it allows you to make those scripts callable from Python. So you can sort of have some elaborate scripting on the Python side and then call the instrumented methods, instrumentation functions in JavaScript at your convenience. But nonetheless, that's the basic functionality. And so that's Frida. So now let's talk about dynamic unpacking strategy. So we have a VS device, and we have Frida, and we have some semblance of idea how to use it. So what do we do? There are two essential strategies in dynamic unpacking. I guess two broad strategies. One is you understand your packet a little bit. You identify a point in the execution flow when it has finished the unpacking original DEX, and then you hook whatever is the nearest function to that, and just dump it from memory or copy it from the file system, depending on where it unpacks the original DEX. That is a very common way to deal with packers, but that requires you to go and reverse engineer it a little bit to get a bit of understanding of when exactly is it finished unpacking, and especially if it's a third generation packer, where in memory does it unpack the original DEX. Strategy number two is a hackier one, but it is very efficient. It's efficient for first and second level, or mostly for second generation packers. And what it does, it just lets the program run, doesn't matter. The program will probably be hanging in just running, displaying you some piece of user interface. Just let it do its thing, and then you just scan the memory for dexes, and if you find a dex, just dump them. The problem is that aside from the actual class's dex, there are plenty other, let's say, helper dexes present in the memory. One is, for example, the packer's own class's dex. Another is maybe some stuff that's been loaded by the system implicitly. So you will likely dump a bunch of dexes this way, and you'll have to then examine them and to find which of them corresponds to the original class's dex. And there's already exist a nice, there are actually many projects. This one is that is usually my to-go project to try. It's called Frida Hex Dump, Dex Dump. It does exactly that, and we'll look at it in a minute. But before that, I just want to briefly describe the details of this strategy. First thing we need to know is just a little bit about the DEX format. DEX, these are essentially the first fields of a DEX format. First, you'll find this magic number, magic bytes. It's DEX, then a new line. Then there's three digits after that that define the version of DEX, and then a null byte. So every DEX file starts with this sequence, and these three can change. The second is the checksum, and it's an Adler32 checksum algorithm of the contents of the whole file, excluding this field. So from the offset OXOC to the end of the file. And the third field is file size. The file size is just the size of the DEX file. And as you might have guessed by now, these are enough to successfully scan the memory and dump the DEX files from there. How do you do that? Well, you scan for this. Luckily, Frida provides you with a wildcard pattern matching convenience functions. So you can find these in memory. Then you look at the file size and you learn how many bytes that DEX occupy, and you copy this many bytes starting from here to wherever the file size, wherever the number in the file size. And most of the time, this will do the job. If you want to be extra sure that what you're dumping is a coherent DEX, you can look at the checksum and calculate the checksum of what you've just dumped and make sure that it coincides with the one in the header. That's what the system does upon loading APK. It's fairly straightforward to do. An evident problem with this approach, I should mention it straight away, is the third generation packers and some other commercial packers. They actually are aware of this approach, and they prevent you from dumping their DEX files. They remove DEX headers, for example. Why do you even need a DEX header? You need DEX header so that the system could successfully load it into memory and then prepare the memory for execution of DEX. And if your packer does that for the system, then technically you don't need a header. So some packers have these manual loading routines that bring the memory to the required state required for running an app and execute it. And you don't really need any headers. So headers might be absent, therefore searching for this magic bytes sequence won't work. Another approach includes encrypting methods, encrypting bytecode, and encrypting various parts of the DEX so that it is never fully in memory, so that you don't really know what to copy. And unfortunately, there is not an easy way around those things. You have to do something elaborate. You either have to reverse engineer it, or you have to you have to engineer a more elaborate dumping routine that would, for example, constantly dumping something something from memory and verifying that it might be DEX bytecode and so on. Okay, so and in conclusion, I'd like to quickly show you. I'm sorry. I'd like to quickly show you this. This technique of searching and dumping DEX files in memory. So Frida DEX dump, it's not the only project that does this. There are many projects and most of them work well. Its Python code is an elaborate version of our toy script. It has a lot more code, but these are mostly convenience function. The most interesting bit is the agent.js, where all this dumping code is. And again, it's not that important to know the details of the script, but just to get the idea of what convenience functions Frida provides you. And you can take this project as the basis for your own unpacking script. And adapt it for your own purposes. So the most important function is here, scandex. Oh, by the way, this is how you make your JavaScript functions exposed to Python. So RPC exports and the array of functions, or hash map of functions, and so scandex scans for a DEX file. And the first thing it does, it accesses the process handle. It's another handle provided by Frida. It allows you to call process-specific functions. This one allows you to enumerate memory ranges. And then it iterates over those memory ranges. And it takes another handle called memory. It's also provided by Frida, available by default. You don't need to specifically instantiate it. And you can call scansync method, which performs the wildcard search. These bytes right here are exactly the magic bytes. So ASCII code 64 is D, 65 is E, 78 is X, so it's DEX, new line, and then the version, and then the null byte in the end. So this code essentially finds all the occurrences of the magic byte sequence for DEX files, and then it performs various validations, which in the interest of time we won't cover. And then it just proceeds to extracting the size, the file size from the header. So you get this and puts them into this results hash map, or rather it's a list of hash maps. And at the end of the day, it at some point writes them onto the folder, the same folder where you run the script from. So that's the idea. And just to show you quickly how it might look like, let me see if something. Okay. One of the samples in the shared with you will be this Com Smarter College Maker APK. It's another toll fraud app. I told you all my examples are toll fraud, and and it is packed. Essentially, that's the thing. It is packed, and let me stop sharing for a brief moment. I forgot to prepare something. I apologize. I apologize for that. Okay. All right, we're back. And let's load this file onto JetX and see what a packed file looks like. So the entry point is this stub app. This application is packed with a commercial packer called Chihu 360. And here we go. That's the original entry point. That's the class that is first to be executed. It's a bunch of native declarations. As I mentioned, most of the unpacking code lives in a native library called libjaguso, and it's a fairly cumbersome, library with multiple layers of protection. So that's what we have. Oh, one important thing to remember is let's decode it. As you remember, I mentioned that packers compress and transform the executable code, but they typically leave all the resources untouched, or at the very least, the malware manifest must be untouched. Why? Because malware manifest is the only opportunity for an app to declare its functionalities, permission, and whatnot. So even if you're dealing with a packed app, it's always worth taking a look at the manifest. And this is a toll throat app, as I said, and simply by just looking at the manifest, we can actually find. We might be able to find something something curious here, and unless it's not the sample I'm thinking about. Oh yeah, it is. So here, it has the notification listener service. The app itself, if you load it into a VM, you'll see it's a sort of a photo editing app, and it has this notification listener service, a photo editing app. And remember that you can use the notification listener service to intercept incoming SMS messages. So although this app is packed, it is still have these sort of suspicious artifacts. And a matter of fact, not only you must declare in the manifest that you have the notification listener service, but you have to declare exactly what is the class that is your notification listener service. So this is a good thing to sort of take a note. That's the service that we might watch out for, what we look out for when we dump our decks and we analyze it. So okay, that's just a little remark on the fact that the app is packed. There's still some crucial information that is available. Now let's ADB install. For some reason, for me, autocomplete doesn't work when I call ADB. So I first call ls, and then I do ADB install. Oh, and do not forget the extension. So it is installed. Let's close our previous example. Let's go into our apps. This is this application. It is installed. We just launch it. We just let it execute. If we see it executing, which means it successfully unpacked itself, and hopefully, if it's not a complicated, it's not too sophisticated, hopefully the original DEX is right now in memory. So it's right now it's time to scan it and just get the dump the dexes. So here I've already cloned the repository, free the dex dump. Go in. What we need is the main py. It's a Python 3 project, so you just Python 3 main py. It you don't need to provide anything else. It starts scanning the foreground application. The foreground application, but make sure the application you want to unpack is a foreground application, and just run this thing. And so we run this thing. It tells us that it's found the target, and it tells us that it's found a bunch of dexes. Guess what? There's only one original dex in here. But you can see it dumped a bunch of, in fact, how many? What? Oh, I'm sorry. Eight dex files. Where does it dump it into the same folder? It creates a folder with the application name, and all the dumps are here. So, and realistically, you're going to have to go through all of them to understand which of them is the actual original dex and which are the supplementary dex files that you're not really interested in. One heuristic that I can tell you is that start from the largest. In fact, I think S is the flag we need. Start from the largest. The largest one is the likeliest one to be the one you're looking for, and then continue in the decreasing order. It's not always the case that the biggest one is the one you're looking for, but more often than not it is. And okay, so let's take a note. It's D12A4000. And let's load it to JADEX and see if, yeah, that one. So let's get back to the Android manifest. And let's see what was the name of the notification listener service. For modern toll-throat samples, as just a remark, for modern toll-throat samples, notification listener service is a good starting point for analysis, just keep in mind. So, okay, COM, smart circle, make a notify service in service. Let's see if that class is present. COM, smart notify service and service. It is indeed present, and it is indeed the original dex, or one of the original dexes if it's a multi-dex file, multi-dex APK, because remember there might be more than one dex. Which one do you need if there are more than one dex? The ones that contain suspicious code. If you're performing an in-depth analysis, then you need to analyze all of them. Here's the notification listener service. It has the on notification posted. It's a textbook example of the SMS interception. Remember, it extracts the package name that issued the notification. It compares it to the default SMS package. And yeah, puts everything into a string and then passes further to the application. But clearly that app has been unpacked, and that's really sort of a quick and dirty way to deal with packed applications. And this slide deck contains a bunch of links. Various free tutorials, really nice introduction tutorial in 5 parts. It covers, I think it covers everything that one needs to know. Then there's a curated list, curated GitHub repository of various Frida resources, useful scripts, projects based on Frida that are also open source that you can study in your own time to get a better understanding of how to hack Android apps with Frida. A couple more articles. Then this one is a GitHub repository of a simple open source packer In fact, it's a second generation packer that unpacks stuff in memory. It's a very, very interesting topic. It's a very interesting kind of packer. And it's simple enough to so that you can understand it in a relatively short time. So I encourage you to read, open up that project and then just read through it in your own time and to understand exactly how it works. Then some other Frida related articles, and in the end, there are two articles by two security companies, one by Fortinet and another by Zimperium, who specifically talk about defeating packers with Frida. And the last one talks specifically about commercial packers and specifically native packers. In fact, they talk about Chico 360, the one that we've just dumped. And that's all I've got for you. And I'll be happy to answer any questions.
Awesome. Thank you, Vadim. So great talk again. And I would, first, there are a couple of questions in the chat. Second, obviously folks on the call should feel free to ask questions as well.
Let me see. So the first question on chat is there a readelf objdump-like tool for DEX files? Good question. I don't think so. The closest to that is AndroGuard. It's spelled like that. It's a Python library that provides you APIs to parse and manipulate DEX files. So that's the closest to that. And you can easily do something readelf objdump related based on that. Objdump, well, readelf simply dumps the section information, and AndroGuard can do that. Objdump, typically, that depends, right? You can always load your DEX into your favorite hex editor, decompress it with the APK tool, loads to your hex editor if you're interested in hex. And if you're interested in disassembly, then I'm afraid there's usually too much Smalley code in there to just use something like objdump for disassembly purposes. The one thing, someone's probably mentioned that already, but just a reminder that a lot of apps have a bunch of SDKs, ad SDKs, monetization SDKs, all sorts of things, the social media SDKs of Facebook, Instagram, Twitter, whatnot. So the user code might actually be a really relatively small portion of an app, and you really end up having a bunch of code, a bunch of resources, and a bunch of strings. So I'm not sure how well will something like readelf objdump works. I think elfs are a little bit more compact. What I do is I unpack an APK using APK tool, and then I grep through things. That's what I typically do. Let me read another question from the chat. For commercial packers that happen to be widely used by malware authors, does it make sense to understand the packer statically as opposed to running the packer and seeing what happens? Yeah, so first of all, yeah, the problem with packers, as with obfuscation, is that legitimate apps do that too. And in fact, thinking about it, I believe I see more packed legitimate apps than I see more obfuscated apps, legitimate apps. So packing is a really common thing. And so that's why unpacking is important, because as a malware analyst, sometimes you need to give an answer. You need to answer a question whether the application you're looking at is malicious and benign, and you have to get through packing. The advantage of static approach is if you want to scale it, if you want to efficiently unpack hundreds of thousands and millions of APKs, that is advantage. Other than that, if you're doing just a review apps one by one, as you know, typically a malware analyst does, then it might not be worth investing your time into writing static unpacker, because it may take, at best it will take weeks, but it will probably take months.
Awesome, thank you. More questions from people?
I was sort of wondering about something else. So on ELF binaries, to make it more difficult to reverse engineer, we strip the binary. So why is it that in Android, like people have gone the exact opposite direction?
I don't know the answer to that question, but it is indeed a good observation that not only Java apps, but a lot of sort of these managed interpreters, .NET, for example, they preserve a lot of that information. Part of the reason is that the internal, they just use those names for the reference, as a reference for in their internal structures. So if, for example, why is the name of a class still available? Well, because some part of the class resolves that class, some part of an app resolves that class by name. So that's a name is a natural sort of a unique, if you will, unique identifier for that class. That's part of the reason, but I'm not sure if that is the main reason. But it's important to notice that many Android apps use layout obfuscation, which actually removes all those identifiers for them. In fact, ProGuard, or as it's known today, R8, is as far as I know, is essentially a part of Android Studio. You can obfuscate it using this obfuscator from your Android Studio and remove all that information. Yeah, that's my answer.
So there's one last question in the chat, Vadim. Then I suggest we take a break. So the last question from Samid is, how does malware obfuscation differ in terms of techniques as compared to legitimate obfuscation? Obfuscation by legitimate apps.
So I'm afraid the answer to that is most of the time it doesn't. They use commercial obfuscators and commercial packers just as well as legitimate application use commercial and you know, just widely available, not necessarily commercial, maybe open source too, but widely available obfuscation techniques. And that poses a problem because I wish that they used different protections. That would have been the way we would have detected them with great efficiency. Sometimes malware folks would use some kind of custom packers. They are typically then that's what goes into a detection signature, the packer information essentially. So it's a sort of they're really sabotaging themselves by writing a custom packer. Although it's a nice engineering feat, but ultimately gratuitous in my opinion.
Great. Well, thank you so much, Vadim, for another great session. So we will take a break. It shows 4:53 on my clock. So we'll come back, let's say at 5 o'clock, 7 minutes, quick break, and then listen to 2 sessions from Roman. And Roman will take us through to the end. So 7-minute break. Thank you again, Vadim. Great talk.
Thank you, folks, for your attention and for great questions. It was a pleasure.
Welcome back, everyone. We're now down to the home stretch. And our next speaker is Roman. So Roman, he's going to be speaking about botnets. Very exciting. So looking forward. Over to you, Roman.
Yeah, thank you. So hello, everyone. Welcome to the training on botnets. That's actually one of my favorite malicious behaviors. I really like reversing them, investigating all this kind of stuff. And it will be kind of joint training session with the next session on exposed framework, because during the next session we will create an exposed module for one of the apps that we will take a look during this training. So let's start. And here is our agenda for today. It's pretty simple. We'll start with definition, then we'll go through several, like 3 examples of DOS botnets, and then we'll go through 2 examples of proxy botnets. So let's start with definition. Android security doesn't have their own definition like of botnets that's widely used, so I took it from Wikipedia. Botnet is a number of internet-connected devices, each of which is running one or more bots. Botnets can be used to perform distributed denial of service attack, steal data, send spam, and allow the attacker to access the device and its connection. So here I highlighted 2 most common, 2 major behaviors of Android botnets that we investigate and we see a lot. And we're interested mostly in discovering more apps with this behavior. So I'm talking about DOS and accessing to the device connection. Yeah, let's take a look at, and we have our own definitions of this kind of behaviors. So as for DOS, we go with code that, without the knowledge of the user, executes a denial of service attack or is a part of distributed denial of service attack against other systems and resources. And in general, by denial of service attack, we mean when the app sends excessive number of network requests to some third-party server. So yeah, that's pretty simple. And here's our definition for Trojan. Code that appears to be benign, such as a game that claims only to be a game, but that performs undesirable actions against the user. And I need to elaborate a little bit more on that. We'll go back to the botnet's definition. The second behavior that I highlighted is access to the device and its connection. So that's what we mean when we're talking about proxy botnets. So in general, it's some kind of usually like real app, like game or utility app or something like that, that has some SDK embedded, and that SDK turns the infected device into an exit node. So the bot owner can use that device as an exit node for network connection. So that's kind of similar to what can be done with like Tor, but it usually happening in like in real apps hidden from user against like, without user knowledge. So and that can be really dangerous for the user, because user they can control which traffic exactly will be sent through their device. It can be something, yeah, something bad happening. And most of these proxy Trojans actually used for different web scraping operations, for spam. They may be used for some DOS attacks and so on. So yeah, that's why we are protecting our users against this kind of botnets. Yeah, let's start with DOS botnets. And the first example that we will go through, it's known externally as Turkish clicker. So in general, its behavior looks like the app will schedule malicious code to be executed every 1 minute. They call schedule at fixed rate. Then malicious code will connect to the C2 and we'll try to get some response. Then if it was able to successfully connect to C2 and get response, get some details on the attack, it will also try to download refer and user agent that will be used during that attack. And after that, it started sending GET requests, so it can load this URL through load URL method, or just like make HTTP GET connection in different way. And the app will try to do it again in 1 minute, and again and again. Yeah, so the app doesn't use any like rare methods, any unusual, I don't know, like anything. So all of these methods in general are pretty common in apps. I think that almost every app has like load URL method in the code. So yeah, and here you can see that we were actually able at some point capture C2 communication for this PHA. And here you can see that the app is actually trying to DDoS paypal.com, and it receives fake user agent and refer. So the like attacked server will think that it's something that happening from an iPad. Yeah, let's go to the JDEX and check the app. So here's this app. And if we go to Android manifest, we actually won't find anything very interesting. So it doesn't have any suspicious permissions and so on. So in general, the only thing that they need is internet and maybe access Wi-Fi state, but those are pretty common permissions. So the main entry point for the app will be start activity class, and let's go to that start activity. So here's start activity, and what will happen here? The app will start widget Java class, and then it will like start some activity, but we actually have no idea which activity is happening because the string is encrypted and it's obfuscated, and it's not just base64. It's a little bit more complicated. Another interesting thing about this app, the line 84. In this line, the app will actually like delete its own icon from the home screen, so the user won't be able to start the app anymore. And the app will be actually triggered by system events like boot complete, Wi-Fi state changed, and so Wi-Fi state changed and boot complete. So yeah, let's go to this widget class and take a look what's going on there. Here's this class, and to go, yeah, on create. So from on create method, this service will schedule itself to be executed, not itself, but it will actually execute this method BLGI where on the fixed rate, and it will be executed every 60,000 milliseconds, which is like 1 minute. So let's go to this method. And here we can see that the app will call this method for some encrypted string. Let's go to this method. So it's actually just like regular GET request, and it will return the server response back to the app. So here it is. So then it will split the response. Let me remind you. Yeah, we need this one. Here's the server response that we got. So it was URL, first of all, then some number and cross. Okay. So it will split the response and send it to this method. So this method will be executed in different thread. Go to operation. So the first parameter will be site that then will be loaded in URL. So next steps, the app will make HTTP GET connections to some encrypted server to get fake user agent string and refer. So if the last part of the C2 response was cross, which is true in our case, the app will actually load that URL several times. And if it's not, it's actually the second parameter is number of threads that need to be started, and these threads will basically do the same. They will send HTTP GET request to that web page with fake user agent and fake refer. Yeah, so that's basically it. It's pretty simple behavior, and yeah, the only problem with this app that all strings are encrypted, and we will actually try to decrypt the strings during next training session on exposed framework. So, yep, let's go back to the botnets. The next example that I wanted to show you, we call it xgetter, and I don't think that it's externally known. So the malicious code was part of this SDK used by many different apps to download media files. So every time an app was trying to use an SDK, the malicious code will be triggered. So malicious code is pretty simple. The app will load, will call you load URL for the JavaScript. You can see it, JavaScript is the first bullet point. And the JavaScript will actually load another JavaScript hosted somewhere else. Right now, this JavaScript is not available anymore, but back during the attack, the JavaScript was loading xgetter.blogpost.com webpage. And it can be kind of okay, but the app is doing it again from the on-page finished callback for that web view where initial JavaScript was loaded. So what actually happening as soon as the JavaScript will load xgetter blog post, on page finished callback will be called, and then back the app will load that JavaScript, xgetter.blogpost.com will be loaded again and again and again, and that's how they created a huge DOS attack on blogspot.com. So that's how this HTTP request looked during dynamic analysis. Let's take a look in the code. So it's inscatter.com. So when that team reported to us an attack, they suspected that it's coming from some app, some Android apps, and the only thing that we knew that this app are probably doing excessive amount of requests to xgetter.blogpost.com. So we started our investigation researching for apps with xgetter string, and we'll do the same thing right now. As soon as the app will be decompiled. It's a big app. Okay, xgetter. There it is, and they actually have xgetter string. So let's search for this method usage, and it's been called from here. So unfortunately, JADEX failed to decompile all code, but that's not a problem. That's actually main method of the SDK. So whenever the app from its first party code trying to use SDK, they call this method to download actual media file. So we actually don't care about this method. The only thing that we care is that the malicious method with xgetter string will be loaded without any conditions right after the method will be called. So let's go back to that method. And the method is pretty simple. So here they create a web view, and then for that web view they will call this method, and this method will actually load JavaScript into web view. So here you can see that there is base 64 encoded string, and this base 64 encoded string, it's actually this string. So they just create the big JavaScript and load it. So it would be kind of okay unless one thing. Let's check web Chrome client that they created. No, we actually need to go to web view client. Let's say set. And here it is. From on-page finished, for that web view, they will call this method. Let's go to this method. And that's again. So again and again, the app will be loaded in the same JavaScript that in the end will load some web page. So that's very interesting technique to make DOS attack. I don't think that we ever saw any other app doing it in the same way. So it's, I think they were the first one who decided to do it in this way. And yeah. So basically, because that JavaScript was hosted somewhere else, they were able to change target, which is here, very fast on their site. And yeah. So that's it for this example. Yeah, let's go to the next. We called it Puppy because the first C2 that we discovered was pub.puppy.com, and this malicious code was part of third-party SDK too. It's some advertising SDK, and they did it kind of in similar way. So they schedule. So there are several call chains to trigger malicious code in the SDK. However, every of this call chain will end up in scheduling malicious code to be executed in 6 hours. And then malicious code will connect to the C2, receive some JSON with commands, and load URLs from that JSON. So let's take a closer look at the JSON file. So the JSON will probably have, so in most cases, it will have 3 parts. SRQ will contain the range of hours when the malicious code should be executed. So if current hour is out of this range, the malicious code won't be executed. Next, TI, it's timeout, it's delay in seconds between 2 URLs will be loaded, and the third parameter is array with URLs. So we saw that they were loading only Google search queries for actually many different Google search queries, and yeah, then they were loading these URLs through load URL method and schedule a malicious code to be run again in 6 hours. So in general, it looks like, okay, they have several passes to load this, to execute this code, but it looks like they were going to send this request not very often, at least from this code. But let's take a look at real picture. this is publicly available data from Google search trends for BMW requests. So as you can imagine, actually many people are searching for BMW. It's like famous, yeah, it's pretty popular search query, right? But if you compare the regular data for BMW with the data on the peak of attack, you can see that the attack was actually huge. And yeah, that was really crazy. So it may look like they were scheduling these queries to be run only like a few times, but actually, yeah, there were a lot of these queries. So let's take a look at the app. It's called like yeah. And this is a big app. So when they reported us this attack, they actually wasn't so they suspected a few apps loading search queries in web view through load URL, and they send us like suspicious apps, and this app is probably like DDoSing Google search. So the only thing that we knew at that moment that the app is calling load URL method. So let's take a look at load URL method usage in the app. And it's a huge app. Yep. Yep. Well, so here you can see that actually there are tons of usages, like 338. So during our investigation, we actually had to go through all of these calls to be sure that we are not even anything. But right now we can skip all this part and go to this SR key and TI and US values from JSON. So here you can see that they actually extract this data and send it to the method. So these first two parameters, it will be something that stored in SR key. The next parameter, it's TI, and then string array from US, us. Here it is. So for these first two parameters, they check current data, get hours, and if hours between these first two values, then they send a message here. Oh, yeah, that won't work. Okay, so yeah, because of my remote desktop, I can't actually click on that button, but yeah, the message will be sent here, and this method will be executed. And what actually happened here, they create like a web view with on-page finished callback, which is actually like load URL. And from on-page finished callback, they will load next. They will load like next URL from the array, and that's it. So it's pretty simple behavior hidden inside. Yeah, that's the important thing. That's the timeout. That's timeout, which will be like I in seconds. Yeah, so they send message late. So pretty simple behavior hidden in a huge APK file among other like not millions, hundreds of load URL calls. And yep, that's it for DOS behavior. So in general, for DOS, it's pretty simple. They just need to like load URL and make HTTP GET request. Of course, in some cases, they may try to exploit some different like vulnerabilities in servers and so on. But most of cases that we actually saw, they just like send an excessive amount of like HTTP GET requests to the server, and that's it. And proxy botnets. So these are botnets that that turns infected device into exit node, and they are mostly used for web scraping and spam. So here's the first example. It's externally known as TeamDoor, and if you start analyzing the original app, you found no actually proxying code because the app dynamically loads additional code, something that Vadim talked about before. So the app actually downloads additional jar file and load it through the X-class loader, and malicious code will be actually in that jar file. And so the behavior of that jar file is pretty simple. So first of all, it creates SSH, it opens SSH to the C2, and then enables port forwarding to localhost. And then it listens for commands from C2, like reading lines there. And as soon as it received command to create like a socket, it creates a socket to like some server and some port, and then it just transfers data between those two sockets. So they just create an exit socket and send some data from the C2 to that socket, and they receive commands back. Let's quickly take a look at that app. It called, yeah. So this is TeamDoor APK. That's the app that actually loads malicious jar. We found like actually we won't found anything interesting in this app by itself, except for the place where they load jar file. So we'll go directly to teamdoor.model.jar file. And the entry point, the method that will be executed through the X-class loader is model init. So the only string, so it receives two parameters. One of them is context, and the second one is string, which is actually like app server. So let's go through main call chain for this app. So it will start service, and the service from run will call init, and init. So the most interesting parts for us here is start proxy and start SSH, and we will start with start SSH method. So here they use third-party like code to create a SSH session to the server, and yeah, here you can see like app server. It's like IP address like it's actually like C2 address received from the app itself, and they will compare. So based on this proxy type value, which is hard coded to HTTPS, they will enable port forwarding to the local host for that SSH session, and that's basically it in this part. So let's go back to start proxy. So the second method that I think that I said is interesting for us, it's start proxy, and no, that's stop proxy. We need to find start proxy. So for start proxy, again, they check proxy type. So actually, that's interesting because they check if this proxy type equals proxy type. So it will be like true all the time. So they will start this HTTPS proxy server. Let's go to it. And so it will create server socket and then starts client socket handler method for that. So yeah, that's actually this method. And what it will do. So that's client socket. It's the socket that was created to like local port for like where SSH connection is forwarded. So they like just waiting for command from here, check it, if it matches, it will create new socket here in this line 76, and then for this socket they will like forward data. So that's another method where they like transfer data from one socket to each other, and they have actually like many many places where they read some data from one socket and send it back to another. So yeah, it's not that hard, but like usually it takes some time going through all these like sockets and like making sure that they actually sends one data from one socket to another. But yeah, in the end, they just binds to sockets and transfer data from one to another. And it's something that been done silently, like for the user, so user have no idea what's actually happening on their device. Okay, so back to the Botnet training. And the last example that I have for botnets, we call it internally idle coconut. So it works in similar way. So it creates WebSocket, then it waits for command, and there can be several commands sent, but in general it will create new socket and binds WebSocket to the new socket, transfer data from one to another, and wait for a next command. So yeah, that's actually it. But in this case, it was it has ability to create many different sockets in one time and transfer data correctly among them. And we were able to capture some traffic from this botnet when it was active. And here's an example. So first of all, the app, infected device, will send some data about the device and the app to the C2. So this first part, which is 000, is actually socket ID. And when the app sends some generic commands like initial command, initial report, ping, pong, and so on, all the commands that are not related to the socket, so they will use 000. So the second is actually command. So the first command is report to C2, and they will send some data on the device, on the app. Then the server responds with ping, and the infected device will respond to pong and some additional details on the device. As far as remember, there's some information about current connection and so on. Then server responses, C2 responses to the device, asking them to create a socket to this server, to this port, and then the next command will be chunk to send some data to the socket. So the app will send all this data. As you can see, it's like a regular HTTP GET request, but they prepared all like headers and so on, so they can transfer this data, and the infected device will capture server response and send it back to the C2. So in this example, it was some HTTP 302 response, which like redirect. Let's check the app in the compiler. So we'll So yeah, we'll start with manifest, and it's actually like regular app. It has pretty huge manifest, but nothing really suspicious here. So let's go to the entry point. And as you probably know, that's the main entry point of an app because it's set as an activity content filter like main launcher. But that's very interesting. There is another method will be called before that main activity, and it is listed here under Android name, and the method called learn application. So there is a possibility for an app to load some code before like actually main activity being loaded. It's usually used to initialize some libraries and so on. So let's go to this learn application method and English learn application. Here it is, and on create. And as you can see from on create, the app actually initialized lots of different third-party SDKs, like actually many different SDKs, right? And we're interested in this one. That's actually one of several third-party SDKs used by an app. Here it is. So what it will do, it will start coffee service. Let's go to the coffee service. And from onCreate, it will call this method, which actually, like not method, will create this object. Let's go here for the new. Yeah. Yeah. So whenever it's scheduled to run, it actually will create WebSocket. So this code is, I think it's some kind of third-party SDK, or maybe it's a little bit modified third-party SDK to work with WebSocket. So it will create a WebSocket, and then it will send 00 generic and some information about the device, the same thing that we saw in their responses. And they also will set a listener for commands, and here it is. So there's a command that can be sent by the C2 back to an app, like connect, chunk, ping. And for example, for ping, it will be, they set C to 0. And here in commands, they will, for ping, they will send back pong. For one, which is connect, they will create C2, or they will create a socket. It's here. This method will actually create socket. And for chunk, they will send some data and send some data to the created socket and read the server response and send it back to the C2. So yeah, that's basically it. We won't have enough time to go through all these methods to like take a look what actually happened there. So it's pretty big SDK, and I just showed you important highlights about that. But yeah, that's pretty interesting, and we spent some time reversing it and finding, and there are actually like a newer version with a little bit more advanced commands, but still in the end it's doing the same: create circuits, transfer data, sends back response, and so on. Yeah, so I think that's it for my presentation, and we went through all of these examples. You can find them shared, and yeah, another additional example. Another additional example, it's battery X APK. It's pretty simple actually, but it wasn't decompiled correctly by JADX, which makes it a little bit harder to analyze. Yeah. That's it. Questions?
Thank you, Roman. So guys, questions?
I pasted the links to the samples in the chat again. So Roman, maybe you can explain a little bit what people are going to find inside that zip file. I've also seen the request for slides. So I've zipped them up and I'm just sending them to VS and Bill right now in like a minute, and then they can share it with all the students.
Thank you, Sebastian.
So as for archive with samples, here list of file names and SHA-256 hashes for these apps just in case. So yeah, we went through these apps, and this app, we didn't analyze it, and you may have problems with JADX decompiling the app, but yeah, if you will able, if you find a way to decompile it, actually, it's pretty interesting and simple proxy Trojan.
More questions? Fantastic. So thank you, Roman. And how about we take a quick break, 7 minutes or so. It's 5:03 Eastern. So let's reconvene at 5:50 for the last but not least session by Roman on Exposed. So, and learning to use it. Awesome. So 7-minute break, everybody, and then we'll reconvene. Thanks. Okay, welcome back, everyone. And we're now down to the last session. And Roman will present the Exposed framework for reverse engineering. So Roman, over to you.
Thank you. So welcome back. Welcome to the Exposed framework for reverse engineering training. Yeah. Here's our agenda. So first of all, I will introduce you to the Exposed framework. Then we'll discuss how it can be installed. How it can be installed. And in the end, we will go through its capabilities. We will discover where we can find more models. We will find out how we can create new models, and we'll try to create our own model for that obfuscated sample from Botnet training. Okay, let's start. So repo.expose.info looks like official website for Exposed, but it wasn't. It doesn't look like it's been updated recently. So I suggest you to like go to XDA Developers Forum, and if you want to find more information on Exposed and like find some support on Exposed and so on. So I think that it looks like XDA Developers Forum is the main page for Exposed framework. So what is Exposed? Exposed is a framework for models that can change the behavior of the system and apps without touching any PK, without like, patching or anyhow modifying any APK. And all changes are done in the memory. You just need to deactivate the model and reboot the system to get your original system back. And yeah, you can implement multiple models that can do changes to the same part of the system or app altogether. Yeah. So yeah, that's basics of the Exposed. And let's take a look at some pros and cons of Exposed. So Exposed framework isn't actively developed anymore. I don't think so. I wasn't able to find any Exposed framework version that will support like newer versions of Android. The latest supported Android version is Android 8.1. But yeah, so another problem that whenever you want to load or update your model, you will actually need to reboot the device to make changes active. And the reason, according to the web page, according to the to some materials that I found, Exposed framework is not being actively developed anymore, mostly because it can be detected by other apps, especially by SafetyNet. So yeah, I'm not sure how SafetyNet detects it, and so I can't advise on that. But as for other apps, if they use, if they check for like files, existing files or something like that, you can always hook these methods and like prevent them from detecting expose. So for most third-party apps, it's not so hard to prevent exposed being detected. So, and for cons, exposed, so even for those apps that rely on safety net APIs, you can probably try to use Magisk, and Exposed is available as a model for Magisk. The Magisk, they call themselves as fileless framework or something like that. I didn't try them because like I never had problems with like safety net detection. Okay, they can detect exposed, but that's not a problem for my purpose. So yeah, so the thing that I like most in exposed, that you can write models in Java in Android Studio, like a regular app, and that's really great. I like Java. You can use Kotlin too. It's very stable. So at least for my purposes. So as soon as you will be able to like run it on the device, all models are usually pretty stable and works great. While with Frida, for example, in some cases I had some problems, and yeah, it's not that stable. I think that it's exposed usually more stable than Frida, at least during my tests. And it's very powerful. You can use different Android APIs inside your models. So, yep. Let's take a look how it actually works. So exposed models, so exposed framework actually been injected into Zygote, and it injects all models into Zygote. So it means that it will be part of every app's process. So yeah, you can hook any existing method from system or third party apps. It means that if you want, you can hook load URL method from WebView. If you want, you can hook decrypt method from an app. But there is a limitation for that. You can't hook methods that will be loaded dynamically. So if the method is not existing at the moment when model being injected, when the app is being loaded, it means that yeah, you won't be able to hook it, unfortunately. So yeah, you can inject your code. So basically, model allows you to inject some code without actually modifying an APK, and you can inject your code before or after the method will be executed, and you can even like completely replace the method. So you can modify arguments for the method, and you can modify or just read the return value from the method. And you can also like filter out all calls from uninteresting apps for you, and just log and hook methods being called only by some specific package names. Or you can do it for all apps. So yeah, that's it. And so that's basically it about exposed. It's pretty simple and yet powerful. So let's start with installation. So for this training session, I created Android emulator image that will be shared with you. Before that, I actually used exposed on the real test device with Android 6, and it was really easy to install it. However, it turns out that it's way harder to install exposed on the emulator image, especially on like Android 8.1. but yeah, I did it, and here you can find some instructions. So first of all, I created Android emulator image. It's x86 because it's way faster, and I used API 27, which is Android 8.1. And I decided to create an image without Google services because that's the easiest way how I can use ADB as a root. So by default, I think every Android image without Google services, you can use, you can call like ADB root, and ADB will be restarted as root. So that helps a lot. So the second thing, you need to root your emulator real device. I found an interesting article on that. So first of all, you will need to load your image with writable system and Linux permissive options. Then you will need to push subinary into the system and install SuperSU. So the only difference, the main problem in that article that I found, if you update SuperSU for that image, so at least it was a problem for me. Whenever I tried to update SuperSU, my image stopped loading and I wasn't able to use it anymore. So I had to go back to the beginning and install it again. So just do not update SuperSU, at least if you're using my image. And you also may need to run ADB root or ADB shell su daemon after every reboot. But I don't think that in my image it works good, at least during my tests, but maybe in future it will be a problem at some point. I don't know, and I'm not quite sure if it's really necessary, but it's probably helps. Yeah, I'm trying to load emulator every time with this parameters writable system and Linux permissive. So it helps. Yeah, it helps for some reason exposed to work properly. So as for exposed installation, in general, when I used it before on real device, I just had to skip first step and go directly to install exposed app. So you can actually install exposed framework from the app, but I had some problems on emulator with that. So for emulator, I need to download binaries, proper binaries manually, push them to the device, to the emulator, and install them. And only after that, I installed exposed app and rebooted the device again with that permissions. So after that, I had exposed running correctly on the device, and I was able to use it and start working on models. So yeah, let's talk about models. And by the way, here on screenshot, you can see the green, image showing you that the exposed is running and everything is probably correct. So there are actually tons of different models were created by the community. However, most of these models are not for RE purpose. Most of these models were created to modify some system UI, or I don't know, to add some features to Android and something like that. So most of these models won't be interesting for RE purpose, but I'm pretty sure that if you search enough, you will find something interesting for RE too there. But I'm usually creating my own models whenever I need them. There's a great article from the author of Exposed with detailed explanation on how to create your own model. And you can read the documentation on Exposed Framework API by that link. So I actually went through that article and highlighted a few things that are already outdated. So you can basically use that article, but a few things there, unfortunately, outdated because it was written, I think, maybe like 4 years ago or something like that. So yeah. Yeah. So first of all, you need to create Android Studio project. It is not a necessary step to create an empty activity, as far as I know, but it's way more easier to create an empty activity. And you can choose many different like minimum SDK versions. I suggest you to use minimum SDK version 16 because it's more stable. I think that exposed models with that version works more stable, but you can actually try different versions. So as a next step, you need to add exposed interdependencies. So you need to modify build.gradle file. And that's important step, not to modify the correct build grade file. There are actually two build grade files in the project, and you need to modify the one that is an app folder. And you need to add the two lines under dependencies. You can see these apps, these lines here. So after that, in article, they suggest to turn off instant run, but you don't need to do that anymore. It's not a problem anymore in current Android Studio versions. So next, we started working on our code. So first of all, you need to modify Android manifest and add this part under application part of Android manifest. So in general, yeah, the first data is about exposed model, that it's actually exposed model. The second part, it's about description. You just write some description for a model. And then exposed minimal version. So they promised backward capability for all versions. I usually use 82 and it works okay. So that's it. So then you need to add your first class for the model and link this class into exposed init file. So first of all, you need to create assets folders and put create exposed init file there and put your class name into exposed init file. And that's it. You can write last step. Yeah, right. Last step. So as you remember, we created an Android Studio project with empty activity. So whenever you will try to run it from Android Studio, Android Studio will will show you an error that it can't launch. It can find proper activity to launch. So you actually need to change launch options to nothing. So that's how it can be done. And yeah, now we can write the code. So first of all, you need to add some imports to the class. Then your class need to implement exposed hook load package interface. And it means that it also needs to implement handle load package method in the class. And that's it. Inside that handle load package callback, you will actually be able to write your own code and put your own injects there. So it receives load package parameter, LP, and the package name of the loaded app, of the app that you're trying to hook, will be in this load package parameter package name. You can also use exposed bridge.log for login, and you will be able to see these logs under logcat, and you can see, and you will be able to see these logs in exposed app too. And you can also use regular logcat, like log.i or something like that, regular logcat output too. And then you need to add find and hook method to actually hook methods. And quick reminder, exposed unfortunately can't hook dynamically loaded code. So you need to be sure that your hooked method will exist at the moment of the app, when the app will be loaded. Otherwise, your model will fail to execute. So inside this find and hook method, you can implement 3 methods before hook method. It will be called before the original method. So here's a place where you can put your code that you want to execute before original method. And after hook method, it's a place for your code to execute after original method will be executed. And you can put your code in replace hooked method to completely replace some method. And you can access actually hooked class from these methods. It will be under this object. You can access arguments. It will be like an array of arguments. So you can't hook generically all methods with the name. You will have to create separate hooks for like every method, listing all available arguments. And you like so whenever you are inside the method, you actually knows the right amount of available arguments. Yeah. So you also can get return value by calling get result and change return value by calling set result. Yeah, that's it. So let's go to the manifest, to the Android Studio, and I will show you all the things. So it may sound too complicated for the first time, but it's actually pretty simple. So let me show you yeah, I need to make it bigger, right? How can I change? Maybe I can do it like this. Yeah, sorry about that. I forgot that it's not. Does anyone know how I can change fonts, make them bigger in Android Studio?
Try maybe settings in this menu, file settings. Yeah.
Let's make it chemical. Is it okay right now? Can you see it correctly?
Yep,
awesome.
very good.
Awesome. So as I earlier said, there are 2 build grade files in the project, and here's the lowest one. You don't want to touch that file. Believe me, I spent lots of time investigating why everything is not working as I wanted. You need to actually modify the build Gradle file, which is in app folder. Here it is. So you need to add 2 lines under dependencies. Then you need to modify your Android manifest, and under the application you will need to add the following lines. And so you also will need to create the assets folder and expose to init file, and you need to create your class. So in expose to init file, I just listed my class name, and that's it. So that's the class. So here you can see imports. The main class, and it implements exposed hook load package interface, and it implements handle load package method. So this method will be called every time a new app is being loaded. So here you can see I just load in. I just log in that some app was loaded. So let's take a look at the app that we are interested in. So we want to deobfuscate this app, right? So we want to hook this method that decrypts strings. And what we can say about this method, it's part of encrypt class. It's called decode, and the parameter, it has only one parameter string. So let's go to the code. So first of all, at this point, we want to filter out all apps except for our apps that we are interested in. And then we want to hook the method, find and hook method from encrypt class, which called decode with one parameter string class. So whenever your method that you want to hook have more parameters, you can add them here like class. So if it's global parameters, you need them add like this. Something wrong, isn't? Yeah, okay, it doesn't matter. But if it's kind of internal class name, then probably the best way to do it's like to add them as a string. That would probably work. Yeah. So as a next step, I decided to implement both before hook method and after hook method. And from before hook method, we will log the first argument. And from after hook method, we will log return value. So the thing is about that we can actually implement all of this in after hook method because the arguments won't change and the return value will be already known here. But just to make a good example, I will implement both of these methods. And yeah, that's it for this point. So here's my emulator. We need to install it. I think that was installed. Oh, yeah. Here you can see that exposed module was updated. And let's also install the app. Okay, here's the app. So now we need to reboot the device. So I usually turn it off and then load with those parameters that I told you about. Here it is. So writable system and Linux permissive. It will take a few seconds to load it. So yeah. Let's go to exposed. I think, is it better like this? Yeah, but I can't, okay. I can't click like that. So we're talking about that is exposed main app, and you can actually find everything that you want here. So first of all, modules, we currently have only one module, right? And logs. That's the place where we can see the place where we can see our logs, our output. So, and yeah, let me look at this. So we can see a list of apps that were actually loaded, and we can hook these apps, but our app that we're interested in wasn't loaded so far because we didn't start it, right? So let's go back to the home screen and start it. So nothing interesting is happening now, except for we can't see the app's icon here anymore. So as I told you during Botnet training, the app hides its own icon. So let's go back to the logs, call reload, and sorry. So yeah, here it is. we can see that the app was actually loaded. And here we can see that, first of all, it tried to, so the first decrypted string is market search pname, and it's that string. Let me show you the string in the app. So it will be from start activity. So that's the string. And the second string that was decrypted is AGZL, which is attack.systems/com. Let's go to widget Java. And yeah, here it is. That's the string that, the second string that was decrypted. So if you remember, that's HTTP GET method, and we actually so it tries to connect to the C2 and receives nothing. So when it receives nothing happened, and the app is not executed anymore. So I have a suggestion. Let's dig a little bit deeper and actually modify the method. So then we want to modify this method. So it won't actually try to connect to the C2. Instead, it will return us some results. And we, from the botnet training, we actually know what should be returning to us. So let's go to the Android Studio. I will implement some code. And so for this /com connection to the C2, we want it to return us that URL 15 cross, the same thing that it was returning to us previously, right? So I already decrypted other two C2s where it gets fake user agent and refer from, so we can replace them with some fake values too. So in this case, we hook this method from it's something. So we hook this method from widget Java. It's actually this method, right? And we are totally okay in replacing it. We don't want it to be run, right? So we can just replace it with that. So for other cases, for other attempts, it will work correctly, but when the app is trying to connect to C2 and get some additional details, we will actually send our fake data. So it's kind of almost done, except for one thing. As soon as we will run this model, the app will start DDoSing paypal.com, and we definitely don't want that. So let us replace another method. Let us replace load URL method from WebView. And if we do that without filtering out all packages, like in this space, it will actually hook the method for every app that's trying to call load URL. But in our case, we're interested only in the malicious app. So yeah, what we'll do here, we will actually replace method. And yeah, we will just load URL that we will just log URL that should be loaded in it. And just in case, I just Googled WebView load URL method and found that there are actually two different methods. Can be called. One of them is just load URL with URL, and another one is load URL with URL and map. And in our case, they actually call it with the second parameter. But let's just in case hook both of these methods because we definitely don't want to DDoS PayPal.com. Okay, that's it. Let's run the model. So yeah, expose telling us that the model was loaded. The next step. So the app hides itself from here. So it won't be an easy way to run it. Let's just uninstall it and install again. Okay, it's back. So we need to, unfortunately, we need to reboot our emulator again. So yeah, let's go to exposed, just in case to check that everything is still working as intended. Yeah, here you can see that many different apps were loaded, but our app still wasn't loaded. Okay, let's go to the app. And I don't care what's happening next with the app. Let's go to logs. Reload. And here it is. We can see that the app is actually calling load URL for that PayPal.com domain again and again. I think it's still not loaded properly. Okay, we try again. Yeah, here it is. So actually, we were able to like hook deobfuscation, decryption methods, and we also were able to kind of force the app to work, even in case when the C2 is not working anymore for a long time. We're still kind of able to force the app execute, and we can collect some dynamic signals. So that's very interesting capability of exposed framework, I think. And that's all examples that I wanted to show you. You can find here the code for this. So this is for deobfuscation. This is to force an app to actually work. And here's code to actually hook load URL and prevent us from DDoSing legit sites. So that's it. Another thing that I actually want to mention. So we used exposed breach.log to log our interesting information. You can also call logcat output by log something. And another approach that I tried, and it didn't work on the emulator, but I do remember that it worked perfectly on my test device. You can write it to the file, but for some reason I spent like not a huge amount of time, but I spent some time trying to make it work on emulator, and I failed. So I'm not sure if it probably me doing something wrong, but on the test device, I can't recall any problems with like writing files. So yeah, that's it for exposed framework.
Awesome, thank you, Roman. And you know, we have a few questions. So I see a question on the chat from Samid. And obviously, if you could take that, anyone else who wishes to ask questions can chime in.
Yeah. So question, my understanding, it's a kernel model. So how does the kernel know when a particular function is running the user land without the user process using an interrupt? How can it do this post-pre function hook on user function? So exposed is a kernel model. So exposed framework by itself. Yeah, it's probably kernel model. I'm not quite sure about that actually, but all models are being part of Zygote, and Zygote it's something that actually part of apps process, and all like so you I said that you can use Android API in model, right? But you can't actually use APIs that the app don't have permission to use. So that's the problem. Your model is actually not part of a kernel. It's in Zygote, but it's like in the user space of an app.
Okay, thank you. Yeah, that answers my question.
Thank you, Roman. Other questions?
Yep, I have two questions actually.
Go for it, Chan.
And the first one is that, your demo showing that, export is very powerful, right? So I just guess that, some of the commercial apps, and there should be maybe some anti-exposed mechanism, right? So if not, so suppose that for the Google Play Protect or Google Play, you just using exposed to hack that, and then it will be a lot of problems, very dangerous, right? So do you think currently there are some solutions or techniques to solve this?
Yeah. So the best solutions that I saw, it was actually used by like legit app. So they implemented the exposed detection technique in codes that they were loading kind of dynamically. So they weren't downloading from some third-party server, but it was like local file. They decrypted and they loaded into their space. So the exposed is actually fails to hook those methods, and they were able to do to detect exposed from that part. So that's the problem with exposed. It can't hook dynamically loaded methods. And so by exploiting this weakness, they were able to detect exposed. Another approach that I saw some apps are using, they are using safety net API for like device certification, something like that. And it looks like exposed can't bypass safety net detection. So,
so I guess, yeah, please go ahead. Please go ahead. Yeah.
I was gonna say, was the original question about apps detecting exposed?
John, do you want to clarify that?
Sorry. For me, could you please repeat it?
Oh, I asked, was the question about detecting methods for detecting, or sorry, let me rephrase. Was the question about how apps detect exposed?
Yep. That can be one part of my question. So you know, just for some simple APKs, simple applications, I don't think they have enough knowledge or ability to make their app as robust as possible, right? Just for some big companies and big apps, they have the ability. So I guess that's the main problem.
I was just going to throw out, in addition to what Roman said, one technique I've seen used by, I think, adware samples or ad fraud samples is they purposely throw an exception and then check the stack trace and look to see if exposed methods are called.
Yeah, yeah, I do remember that too. Yeah, great example, Alec.
Interesting, interesting.
Pretty sneaky.
Yeah.
John, do you have another question?
Yeah, I have another question. Is that I mean, just I search on the Google Play. I found there are some exposed installer on that. So because for exposed, it can be the tool to develop the apps or just to hook the APIs, or kind of technically they can also gain your root privilege, right? So how do you define whether this is a benign app or a malicious app? Because I found some exposed apps on Google Play, and their ratings are not that high, less maybe about 2.3. I guess you don't think that's a good score, right? So how do you think? How do you define? You say, oh, this is a malware, or this is just a legitimate app?
That's a good question. I actually never reviewed exposed related apps on Play. So I don't think that exposed framework by itself can be published on Play. I think that it violates Play policies. I'm not quite sure. So as for malware, like answering your question, how we define if it's malware or not. So based on their behavior, if it satisfies our PHA classification, then we will decide that it's a malware. But yeah, so exposed is pretty powerful, and in general, you can implement many different things in models, even malicious. But yeah, I'm not.
Yeah, some of them I think looks good, but maybe some of them doesn't looks that good. Maybe they have the exposed apps installed on their phones, and maybe the hackers can just insert some hidden code inside that to use exposed to get their password or their credential information. So I guess maybe that can be the case, right?
So the thing is about exposed that if the device have exposed installed, it means that it also has root, right? So it's rooted device. Exposed won't work without like sub-binary. It needed all the time. So it means that the malware can actually trying to use root rights to do bad things too. So by default, you can't install silently exposed model. The user will have to go to the exposed framework app and actually enable it. So in this example, let me show you. Whenever the first time I'm installing the model, it will be disabled by default. So it won't be enabled. So it will be disabled by default like this. So the user have to enable it manually, but yeah, as soon as there are already root rights on the device, and malware can actually use them to bypass that.
Thank you.
Thanks, Roman. More questions?
Yeah, I have one. So I've used dtrace, and this had a lot of similarities to that, and like this was really exciting. Thanks for the talk. I guess my question is about intra-process communications in Android, and can you actually hook onto binder calls as well?
Can you please repeat your last question about binder?
Yeah, so I was wondering, like messages that you receive through binder, can you also hook onto them on exposed?
That's a good question. I can't say for sure. I think that the answer is probably, I'm not sure. Yeah, so I'm not sure. I don't think, I actually think that it won't be probably possible, but yeah, but you need to try to be sure about that. But I think that, yeah, it's not possible.
Yeah, I'll try it. Thanks. Thanks.
Any other questions? Well, if not, I will bring our 3-day session to a close with really a very, very warm set of thanks to all of you. I know that in addition to the fact that you guys have spent 3 days with us, putting these slides and materials and samples together in such a coherent way must have been a huge amount of work. So I don't think I'm speaking just for myself. I've got several emails from some of our students telling me how much they enjoyed this sequence of lectures over the last 3 days. So, really a very, very huge thanks to all of you. Sebastian for taking the lead on the Google side of working with us on putting this course together. But really all of you, you guys have at least educated me a great deal, and I'm sure many of the students as well. So Roman, JJ, Arthur, Vadim, Alec, I hope I didn't miss anybody. Thank you guys so much for this. And, before I forget, if you'd come to Hanover, Bill did a good job of selling Hanover during one of the breaks. But if you'd come to Hanover, we'd have had the opportunity to take you guys to lunch and dinner and, sort of wine and dine you, at least to the standards that academia permits. But, we would like to send you some Dartmouth swag, so for that we need, please do send your sort of shirt sizes to everybody, to Sebastian, who can then shoot that over to me. And we'll send you some stuff that hopefully you'll like.
Already started collecting those. Also, thank you for your words, VS. I also want to thank everybody, in particular the instructors, who put a lot of, really a lot of work into that. So also from my side, thanks to Roman, JJ, Alec, Arthur, and Vadim. And also, of course, to all the folks who were here for all the sessions, or most of the sessions. And so it was an intense 3 days. A lot of topics discussed, a lot of knowledge transferred. And so I really hope, first I hope we can actually visit you guys one time in Hanover. But the whole thing was just a great experience. I wonder how it would have played out in person with more labs and more everything. But it was intense, so it definitely is a great amount of material, and we're looking forward to seeing how the recordings turn out.
Yeah, so we will, put all that on a Dropbox site for this, just for the students to know. Sebastian's also sent me all the slides, so I will make sure that the slides are shared with all students who have participated in the course, later today or latest by tomorrow, because my brain is also sort of quickly degrading today. But certainly by tomorrow, we'll have that up. So the students will have that. And as soon as the recordings are ready, we will share a link for those with all of you. So all the folks, both at Google as well as those at Dartmouth. So again, huge thanks to you guys. You can see a bunch of thank you notes, scrolling across the chat. But really, for those of you who are still here, Roman, Vadim, JJ, Sebastian, really, I can't tell you how much we appreciate this. Bill, would you like to add a few words as well?
Well, VS, you've said it very nicely, and I just want to reiterate, my complete thanks, okay, for all the hard work, for all of the examples, for in fact customizing this to the Dartmouth students. As I've seen here, on the chat window, is that not only have you provided them information, but you actually have provided them with an impetus for their future research, all right, which is really important as we go forward, as we look to the challenges that are facing us with regard to securing our digital future. I cannot thank you enough for the time, effort, and the information that you have conveyed.
All right, thanks everyone again. huge thanks. And I'm going to sign off what's been a fascinating week for me and for many of the students. So again, a million, Sebastian, Alec, JJ, Vadim, Roman, and Arthur. Really wonderful job. And huge, huge, huge thanks. All right. So with that, ciao, bye-bye. And
Bye-bye.
great weekend. And hope you guys, the fires start calming down soon and you guys can breathe okay.
Looking better already. It's looking better, but thank you very much. All right. Bye-bye, folks.
Bye.
Bye-bye, Sebastian. Bye-bye.
Weekend.